those proofs within the handler.
Awesome, thanks.
So I have a question. First, thanks for the talk. I really enjoy it. I wonder, one of the key tools we have in HCI to make things easier for people is adding restrictions, right? So if you compare, let's say, a spreadsheet to, let's say, a C program, right? Like in a C program, you can do almost anything you want, but it's hard to accomplish anything, right? In part because there are so many options, many of which are unsafe. In the spreadsheet, you can do many fewer things, but of the things you can, but for the things that you can do, they may be a lot easier to accomplish than if you were doing the program in C. Of course, not everything. So I guess I'm wondering if your approach, makes it easier by making the system more flexible, or makes it harder by making the system more flexible. You know what I mean?
Yeah, I mean, our main case, which is smart contracts, is kind of easy because it's not Turing complete. So we can run, we can find proofs for most stuff more easily. But we also want JavaX to be later, like a general programming languages. We have the project to compile it to LLVM. So that's why we are already preparing it for when it's a general purpose programming language, and then the user will be able to do whatever they want. And then we have some tools to help them prove when stuff gets harder. But as of now, it's very constrained. It's a very constrained programming language given the scenario we are working in. So to focus on your question is, we already have a very constrained, but we are trying to make it work for the bigger scenario. Like, we have a spreadsheet, but we also want people to be able to prove C if they decided.
I more mean the core concept of which is to provide multiple mechanisms that people can use to prove their theorems, right? And so I mean, just providing that choice might in some cases make it harder, because now people have to decide which of several choices they want to use.
Yes, that is very downside to our approach. First is that as of now, we require the verification to not be part of the actual code, which is not like a thing you would usually do in independent type programming. You would like make it correct by design. We are still trying to see how we support this. So yeah, it's not a bulletproof proposition.
All right, thanks. Chris, you wanted to ask something?
Yeah, I wanted to kind of raise a more maybe general philosophical question about usability for proof assistance, just to kind of get your sense for get a sense for what you think about this. When I was in grad school, I sort of attribute this concept to Bob Harper, I think, but I actually asked him about it recently and he doesn't remember, so who knows. I can just claim it for myself, I suppose. But this concept of that like a proof assistant can be sort of like you can do a practice that I might refer to as revisionist formalization. So what I mean by that is you go in with some kind of understanding of how you might represent your system on paper, or what your program is supposed to do, for instance, but it's perhaps not as clear as it could be, and by the process of encoding it in another system, which sort of forces you to think a certain way, you arrive at more clarity and like a better understanding of the system that you were trying to encode in the first place. Do you think that that's a goal? Is that a usability goal for proof assistance for you? Or do you think like should proof assistance really be there to enable kind of whatever mode of thought is already the way that people are thinking about these things?
I agree with you, but maybe to my point of view here is some kind of from experience, because like I learned imperative programming, then I learned functional programming. Now I have to prove things and I have no idea how to do it. And I would prefer to, while I don't know how to do it, to have a way to have it done, but that is not as that doesn't require like so much investment from me up front. So regarding your question, I think it could be a thing, but I'm not sure how we can do it as of now, because like the bridge between what like regular, quote unquote, regular programmers know and what dependent type programming requires from you is a little bit too wide. And I don't know, I'm willing to see where the Witch project is gonna take us.
Yeah, I think that's really interesting. That to me represents like a big, I think, general point of discussion for this whole community is how much what we're trying to do is kind of enable people's existing ways of thought versus structure ways for people to latch onto and incorporate new ways of thought into what they're already doing. So yeah, thank you for that perspective. It's true that it does certainly requires a much heavier commitment from the user to say, okay, I'm gonna like fully immerse myself in this way of thinking now.
Yeah.
We can kind of take this one step further. You know, some people write programs according to specifications, but I think most people write programs to explore some question that they're trying to answer, right? So they know they want to make a program that satisfies some category of user need, but they're not exactly sure what the user need is yet. And so they're going to write a prototype and then experiment with some users and see what kinds of problems this proposed solution solves, and then iterate on that. And so I think a lot of times people don't know what the properties should be of the program that they're writing, especially the formal properties. And so, you know, I wonder, and so I think that's a great question, Chris, about, you know, can these approaches help people refine their ideas or structure their thinking? Or alternatively, is it really not practical to use any of these approaches until people have settled on an idea that is baked enough, let's say, that one could write a formal specification?
I think this sort of supports April's push towards automation, right? So if you automate a lot of these things, then people can sort of futz around in whatever exploratory manner, whereas the system is kind of there in the background to support them if they ever need to lean on it.
Yeah, that's the idea. Like, even if you're writing something that you cannot put not lots of effort to prove it, you can like have some help proving the stuff you cannot pay the effort to prove as of now.
So I think we should transition to the next talk. So thank you, April. We can give it a little
Thank
round of
you very
applause.
much.
Our next talk is by Alistair Reed. It's called Towards Making Formal Methods Normal, Meeting Developers Where They Are.
Yes, give me a second to get my screen shared. And okay, so I'm working in a team at Google. Actually, Luke is at Cambridge University, but the rest of us are at Google. And we're looking at what could we do, what needs to be done to make formal verification kind of much more accessible to programmers. And we're not entirely sure how many people actually do formal verification as part of their everyday kind of programming job at the moment, but we think it's not very many. And so we're thinking about kind of what would it take to dramatically increase the number of people who are doing formal methods. And by that, I'm really meaning who are productively using formal methods. So it's helping them kind of hit their deadlines, hit their quality goals, and so on. So that's the problem we're looking at. And one of the barriers that we see is how long it takes before you get a payback from using formal. So so you start using some kind of formal method, and you start maybe annotating your code with invariants and pre and post conditions, or writing specifications, or whatever you're doing. And for a while, you're not really getting much benefit from this. And then gradually you start to get some benefit, and eventually you hit a break-even point where you're at a kind of net positive. And so how long does this take? Well, again, not really sure, but I suspect in many cases it's in the months. And this is a problem because if it takes you a long time to see that you're actually getting a benefit, then any risk associated with, do I know how to apply formal methods? Is formal methods a good idea at all? Do I know how to apply it for this particular project? How will my teammates respond to it? All that risk is much more of a problem if it takes a long time to get a payback. And in contrast, I think if you look at something like testing, that generally has a much faster payback. You can see progress, you can see that there's a benefit much faster. So something we've been thinking about that would make it easier for people to get started with formal is to try to reduce the time it takes to actually see a benefit. And we've come up with, I think it was Luke who came up with this very aggressive, and I'm not sure entirely realizable target of 1 week to payback. So first of all, having a period of 1 week before you get some benefit or a net benefit is good, because it means that you don't have time to kind of like fret over the weekend. Oh, maybe I shouldn't be doing this. Maybe I should go back to testing or writing code or something. But the other thing is by having this very aggressive time period, it hopefully as researchers, it's going to really focus our attention on what we're going to do next. We could do A or B. Let's do the one that's going to help with how quickly you can get some return on your effort of using formal tools. So that's kind of like one of the things we're using to help shape our research as well as our goal in itself. The way we're planning to do it is by meeting developers where they are, by which I mean kind of take what developers are already doing as part of their day-to-day work, and then look for things you can build on towards that are close to verification, and how you can adapt verification to be closer to them. And so obviously testing and fuzz testing are things that we can try to build on. And we're hoping here to take advantage of, one, programmers are very familiar with and comfortable with these things that they're already doing. So we're wanting to build on top of that. But the other thing we're hoping to do is if we can bring verification close to something programmers already do, we maybe get some sort of synergistic effect where maybe the work that they do to make their code easier to test or to actually do the testing would benefit formal verification, and conversely, things they do as part of formal verification might benefit testing and fuzzing. So we're hoping for that synergy as well as benefiting from any familiarity and comfort. So let me make this a bit more concrete now. This is a bit of Rust code, and it's using property-based testing, like in the previous talk. There's a translation for those who don't speak Rust, by the way. So this a piece of code written with the prop test library. It's effectively a little DSL for creating tests now. And the way it works is it's going to pick a few dozen pairs of random numbers in the range 1 to 1,000, and then it's going to execute the code and see if the assertion fails. Right, so it's going to execute this piece of code. Sorry, it's going to kind of test this code with random numbers. So what we've done to try to kind of adapt this for verification is we rewrote the prop test library so that instead of using random numbers, it would instead use symbolic values. And so with that, the code looks absolutely identical. It's still the same trivial example that designed to fit in one slide and not take much explanation. But we don't have to change any of the code in order to be able to use this for formal verification. So we can we can take this code and we can verify it either using the CLE symbolic execution engine or using the Cruxmere engine, and we're working on another engine at the moment. And so this is kind of heading towards meeting our goals, in that we're building on what programmers already do. They already do some property-based testing, and also if they write more harnesses like this, they'll be able to use them also for property-based testing, and we can take advantage of any property-based tests that have already been written. So far, I've really been talking about things which concern an individual programmer. But programmers don't work by themselves most of the time. They usually work as part of a team. So there's code review, there's people writing tests, there's part of the code review also often involves static analysis. There's people writing static analysis tools, there's people producing training materials to help people write better tests. And so this is the kind of development ecosystem that exists at the moment. And what we're wanting to do is add formal verification into this ecosystem, and the necessary support in the form of kind of people creating and supporting these tools, the training and so on. So now let's think about what it takes to the problems we're going to face if we think about that ecosystem as a whole. So starting with the individual programmer, there are things to do with how they get started. So they might have preconceptions about how brilliant formal verification is or how terrible it is. So we're going to have to overcome those. Verification tools can be quite complex to use. They can be to configure, can be hard to integrate into a build system. So we've got to take care of those. Now that just gets people started. So that's their first week. We have to kind of make sure they get some benefit in that first week. But then the next week, if they do another week with the tools, are they going to see a benefit? And so we're going to get into things like how actionable are reports coming from tools? So things like if they see an error report or something from the tool, how long does it take them to figure out what the report means and what they can do about it in the code? So those are some issues for the individual. If we think about the team that they're in, then they're if I do some verification and someone's reviewing my code, they're going to be wondering things like, well, how are they going to review the verification I've done? So we've got to make it visible to them. We've also got to make sure that they can actually understand the verification that's been done, because they're going to want to look at it and go, well, that looks like you've done a thorough job there, or maybe there's a verification hole, something you haven't checked yet. And so we need to think about how those are going to be visible and understood by teammates. And there's things kind of like across the team that we saw with static analysis tools when they were introduced into Google. You have problems that you want everyone in the team to agree that there actually is a problem to be solved, or that there isn't a problem in some code. So you need little things like everybody in the team has to configure their tools in exactly the same way. Otherwise, one of them's seeing an error report, the other one's not. So there's issues around that as you organize your team. And then stepping out once more to the people supporting the team, you've got issues about kind of, well, what kind of support are we going to provide? What kind of verifier should people be using? Should it be symbolic execution, model checkers, interactive verifiers? What's the most profitable phase to use formal verification? What particular tools do you plan to use? And if you're trying to decide how much to spend on, well, you want to be able to decide how much effort you should spend on supporting formal verification versus testing versus maybe encouraging better code review. So we're going to need to think about how we can gather the evidence to show that one way is better than another. Okay, so those are some of the issues we anticipate around the kind of in the ecosystem. I want to mention two other things which are of a more technical nature. So the first is to do with tools. Most of the verification tools at the moment are developed by research groups, and they've designed the tools, they've really optimized the design of those for research efficiency. What they've done is they've made the tools extremely flexible so that they can explore many different research questions. And this is, of course, the right thing to do if you want to do research and publish papers and so on. But it's terrible for the user because now they've got a tool which, when it gives them a report, it doesn't know what kind of problem they were trying to solve. And so it has to give a fairly generic kind of indication of the problem it's found. And it has many different configuration options. For example, one of the tools we use, CLE, has over 400 options. And when the other ones we're looking at has more. So CLE doesn't seem to be an outlier in this regard. So tools are kind of very general purpose. The error reports are not quite as are very much up to you to interpret what they mean for you and your code. And so we think actually creating more specialized tools, I think Michael was suggesting this in the questions earlier, a more specialized tool which reduces your choices might make a more usable tool. And I've seen this in the hardware verification, where you get tools that are very narrowly focused on solving particular problems and are actually very easy to use. Junior engineers can pick them up very, very quickly. I also wanted to talk about what Rustin Leno calls the decidability ceiling. So we often use tools like SMT solvers, not just for the decidable subset for which they guarantee that they are able to produce an answer, but actually we use them well beyond that, and we try them with much harder problems. And for the most part, they're able to solve the problem. And which is great. I mean, really powerful tools. But if we think about how, if we have many, many more users, and maybe less of them are kind of like the early adopter evangelist types, then when they start seeing tools which mostly give the right answer, but then sometimes fail, sometimes over a very minor change in the code, this tends to decrease users' trust in tools. And so there's a question of like, can we do something to improve consistency? Or maybe we could do something to help programmers identify what part of their program is causing problems. And so some sort of profiler that identifies the hot spots might be the answer here. Okay. So just to wrap up, so we're talking about how to increase the number of programmers who are productively using formal verification tools. And the plan for doing that is to meet the developer where they are, look at what they're already comfortable with, productive with, things like testing, for example, and try to build on that. And we've got this goal partly to guide our own research, partly because we think it's kind of the thing that users ultimately want, which is getting a payback for any time they invest in using tools fairly quickly. And I talked about some of the ecological and the technical challenges associated with that. So thank you very much for your attention. I'm happy to answer any questions.
Thanks very much for the talk. And I'm happy to, take any questions that people have.
I have a question. So I guess one concern I have with the question of using formal methods to meet developers where they are is to what extent where they are will allow the integration of formal methods. So just as an example, if we had Hatra 15 years ago, we might have said like, oh, memory safety is this huge issue. We need to get better formal verification tools integrated into C and C++, using the tools that people know how to use and are comfortable with, and to give them better memory safety. And like, we've tried that for quite a long time, but I think what we found, of course, through Rust was that like, if you give someone an appropriate framework with where from the ground up they construct their programs with a certain value in mind, like memory safety, it becomes much easier, both from the perspective of the analyzer and from the perspective of the developer, to work together and create a memory safe program. And so I guess I'm just wondering about how you think about that concern, about like how much, to what extent can we reasonably apply today's formal methods to today's tools versus we need to, shift people over to corresponding languages that are built specifically with those kinds of verification in mind.
Right, so we're working with Rust, I guess, in part because we want people who are willing to shift, right, and have already kind of like, shown an interest in greater safety, greater correctness. So yeah, I think that's really why we're focusing on Rust with our work. What we're doing is we're taking tools that have been used to verify C code and we're adapting them. They're maybe working at LLVM code, and so we're adapting them to work with Rust. So yeah, I think we're already wanting to work with people who are willing to change, and hopefully we change them along the way, because as they start, there's the thought within the formal community that as people start writing formal properties down, then it changes the way they think about it and it changes the way they structure their code. And I think we will want them to change the way they structure their code to make it easier to verify, although we're not certain how they should restructure their code yet.
Got it. Yeah.
Thanks, Gabriel.
Yeah, so I had a question. So you mentioned so first of all, great presentation. Thank you for introducing your work. I was wondering, you mentioned that you're making a lot of analogies to testing. And personally, I'm curious about that. So you mentioned that testing is something that people get like see the benefits or see the benefits a lot quicker. And I was wondering, I actually don't know if people like see the benefits of testing. I feel like, or at least from what I've heard, like people do testing nowadays mostly because after many years of people falling over way after the game started, they realize that it's a good practice to keep stability. I'm not 100% sure how people like experience like the benefits of testing within like 2 or 3 weeks. So I was wondering if you could, like, in your experience, what is like how do people see the benefits of testing before like going to a new team with like a huge repo and having to like make a change and have confidence?
Yeah, so I mean, it's probably, it depends, right? So one thing is, if you use fuzz testing, people very often find bugs using fuzz testing. That tends to be at the whole program level. If you're focused more on unit testing, and you're doing it as you develop the code, you will tend to find bugs, and then you'll tend to see that, as assumptions get broken, as someone modifies the code, it stays solid. So I think there is kind of that early benefit. You also get nice early feedback, things like coverage metrics and so on. And incidentally, for formal methods, it's coming up with good metrics like that give you feedback on have you done enough yet is probably going to be important.
Thank you.
Okay, Michael.
Hi. So I'm wondering, so you sort of present an interface to formal methods via this testing library reimplementation. And I'm wondering whether the idea is that you take existing tests, existing property tests, and you run them under a symbolic evaluator, and you find new bugs that weren't caught by the property testing? Or is the idea not that you're going to find new bugs that weren't caught by property testing, but simply you're going to reuse the property testing user interface, as it were, for your symbolic evaluator tool, so that people write new tests that do stuff that they couldn't have done with property testing?
So it's probably going to be a bit of both. I mean, definitely, a starting point is just take existing tests and run them. or use them for verification. And incidentally, some of them probably will cause verifiers to fall over, and there won't be much you can do about that necessarily. So there will be an intersection of there will be tests which are great for both tools, and then some which are only suitable for one or the other approach. And then so we'd expect to find new bugs. So for example, I've been kind of modifying some tests in a project that I work with recently, from standard fixed tests to just using property-based testing. And along the way, I've been realizing things like, it's not just I want to pick two random numbers and test with it, but they need to be two random numbers that have a high probability of being equal now and then. And so a verifier will naturally just go, oh, let's think about the case where they're equal. Let's think about the case where they're not equal, because maybe there's an equality test in the code. But a random fuzzer kind of picking two 64-bit values is really unlikely to hit that problem. So we might find some new bugs, things that haven't been considered as a result of that kind of thing. Was there a third part to what you were asking?
Are you expecting people to write new tests that wouldn't have worked under property testing, but do work under this new symbolic evaluation framework?
I think so, yes. So yeah, I'm not entirely sure what they will be. We're yet, but we certainly, yeah, we're hoping people will go beyond what they'll do in testing at the moment.
Cool.
Jonathan.
It's a great talk. You're talking about giving developers payback within a week really resonated with me. Although I thought this vision is not necessarily limited to just to testing. We've been thinking about similar things in my student Jenna Wise's work on gradual verification, which is in an OOPSLA paper presented yesterday. But I wonder whether ideas like specification, which we're exploring, making kind of more, giving a faster feedback cycle on, that seems to play a big role in property-based testing as well, right? Your example leveraged the assertion statement at the end of the method. So I wonder how, can property-based testing be a bridge towards helping people gain more value out of specifications in lots of different ways?
That's definitely what we're hoping for. Yeah, I think I'm just saying yes, really. Yeah, I mean, one thing that we are kind of conscious of, though, is that property-based tests, or if you just write a bunch of properties about some software, then you're actually never quite sure if you've written enough properties yet, or even that they're consistent. So we're kind of, there's that problem. I mean, classically, it's like, I'll write a specification, it must produce the result must be the square root of the input or something like that. And it completely answers there is one precise answer that is allowed. And with property-based testing, you're never quite sure, have I written down enough things? It's I know it's commutative and it's idempotent and it's but am I done yet? So we're not quite sure how much of a problem that will be. In previous work, I was working on creating specifications, and I remember it being extremely hard work, and specifying realistically sized things took years. I'd like a 40,000 line specification was the short version. I
mean, maybe that just points to the benefit of having tools that can give you feedback on specifications as you write them. Right.
Yes, there probably is a need for something which just looks at your specifications, at the properties you've got, or whatever your specification looks like, and tells you things about what that specification is saying, independent of your implementation.
Okay, thanks. Ellen.
I'm having trouble getting my video on. There we go, right. Sorry about that. Okay, so good talk. So one of the things that resonated with me was this issue with the decidability that you were talking about under the heading of the decidability seedline, of what are the cost models that these various tools are giving you. So it is very easy to make apparently trivial changes to specifications, and suddenly like black smoke comes out the back of your tool rather than results. And I was wondering, yeah, so if you ruled the world, what would we do about this problem?
Well, so yeah, I was thinking that some sort of profiler that kind of highlighted these are the bits that are expensive in your code might be useful. So for example, we're using the CLI symbolic execution engine at the moment, and it basically explores paths through your code. And if you could highlight the bit that suddenly gives rise to 1,000 new paths, then maybe you'd look at that and try to do something to resolve issues there. What I'm not sure about though is would anything you do for one kind of tool actually help you with some other kind of tool? So as you switch from symbolic execution, which suffers from a path explosion, to a kind of a model checker, which tends to suffer from a state explosion, is it the same fix needed for both those tools? And hopefully the answer is often yes, but I'm certain there will be cases where the answer is no, you need to do different things. And now you've got to modify your code in two different ways, which would be unfortunate.
So that, I mean, okay, that's all good. That's things that the user of the tool can do to make their life hopefully less horrible. I was wondering if there's anything the tool writers could provide that would smooth the path for doing this.
So, well, I mean, tool writers have been doing lots of things to make their tools scale better, right? So, they've been doing that. They should keep on doing that. It's great work. But I suspect they won't solve all the problems. And so, the thing to do would be trying to figure out, is there some way to highlight things that the programmer could do, add a loop invariant, whatever it is that they might do to assist the tool. I think that would be the thing to think about.
Thanks.
Great discussion, thanks. I wanted to suggest some vocabulary that we could maybe use to talk about part of this problem, which is risk, right? So I discovered when I started being a software engineer in industry that people always talked about risk. And initially it didn't make any sense to me because, well, either your software is right or it's not. And, there should be no concept of risk. But in fact, you write some software and then you don't know whether it's right. And you write some code and you do some work to try to find out whether it's right, and you convince yourself that you haven't found any serious bugs, at which point there's still some risk because there might still be latent bugs that you haven't found, right? So this kind of gets to this question. It gets to the issue that Alistair was mentioning with property-based testing, right? You can't tell when you're done. So I guess I wonder if we could integrate some notion of risk into these tools. So that people could reason about, what is the probability that there is still a latent serious bug, and what more can I do? Not just what more can I do to reduce that probability, but what's the most cost-effective thing for me to do next?
Sort of our kind of alternative to the kind of a coverage metric that you might use for testing. It's like, oh, these lines of code have never been executed. Well, that seems like the highest risk. I should check those ones first. And then I'll worry about, other things I could do. I'm not entirely sure what good metrics for that would be, at least kind of like how to take something I can measure and relate it to, risk or something like that. I've seen attempts to do it on hardware tools, and the results were kind of laughably bad in that they were clearly giving answers that did not match any intuition. So I think there is a whole issue around, what are the things you can measure to give that feedback to the user? What kind of metrics can you use? I don't know the answer.
So I guess officially we're out of time. And people are supposed to be able to go to other talks until we resume. So yeah, Will's suggesting a round of applause. Round of applause for all the speakers. Thank you, Alistair and April. Very exciting start to our workshop. So we'll reconvene at, I guess I can't actually mention a specific time because it's different times for everybody, but in 40 minutes. I have been told that I need to keep the room open so that the feed doesn't stop. So I'll keep the room open. And if we want to have some discussion here, then we can. It'll continue to be streamed to YouTube, or if people want to, pop off and then return in 40 minutes, or just talk informally in Discord, that's okay. We'll resume the formal program in 40 minutes.
All right, I rejoined the Zoom chat. Whoops. All right, I think that's better. Is anyone over here right now?
Hello.
Hi, Cyrus.
How's it going?
It's pretty good. Hope the weather's good over there.
It's nice and sunny. It's cold, but you know, take what you can get.
Yeah, well, I mean, given how the last couple of months have been, yes.
Yeah. It was 72 until last week here, so whatever.
Oh, nice. Yeah, our 72 is coming this week, and then we'll probably plunge into the cold depths of hell, but yeah.
Yeah, I'm not looking forward to this COVID winter here, at least. We had the outside stuff until recently.
Oh, yeah, Iowa just went back on lockdown.
Yeah, we went back to. Got a big emergency alert text message from the governor this morning. It's the situation.
Oh, there you go. Now I can see video of everyone.
Oh. Well, you can only see video if somebody turned on their video.
Oh, thanks, Michael.
You violated the correctness property.
I don't. My institution doesn't let me use Zoom, so I don't know how all this works. It's all foreign technology to me.
They don't let you use Zoom.
What do you use instead?
Quick question. Does anybody who use Keynote, if you do the thing where you say play slideshow in window, is there a way to do that and also see your presenter's notes?
Okay, the best solution I've found. Do you have another? You have an iOS device?
Yeah. You just bring up the notes there. Okay.
So what I do is I use the remote, the Keynote remote feature on the iOS device, and then you can see the next slide and the notes on the iOS device. Okay. Yeah, that's frustrating. I think it's one of these things where like they probably are well aware that like this is a real thing that people need right now, but it takes time to get these features rolled out. So that's just my theory.
Okay. Got it. Let me make sure I have everything ready to go.
Yeah, thanks for checking.
So Peter, Michael, is Zoom considered a security problem, or did you just don't have a subscription, or what?
Oh man, do I say things on live air or not? Yeah, it was a giant fight. Let's just put it that way. We have limited Zoom support specifically for teaching, but we have to ask. But it was like a security fight type situation. / we paid for something else, and they really wanted us to use it. So
makes sense.
It doesn't make sense for the record. Don't excuse it. I've lost a good couple of months of my life. It's great.
I mean, if I were sitting in IT and I had an IT budget, I had just written a big check to Cisco for WebEx. Like I could see how I wouldn't want to then write a check to Zoom for the same technology that fits in the same category.
That's 100% fair. Do you work for my IT department? Wait a second.
Well, the flip side is, you know, I'm going to guess that the marginal cost to Zoom of hosting more people is pretty low. And so they could say, look, if you have a WebEx account, we're going to make you a special deal to switch to our service.
Oh, that'd be nice. Zoom is really not that. They're all kind of like roughly the same or bad in their own little ways. So it's not that big of a deal, but it was kind of a weird political battle in my institution a few months ago. So
I can only get Zoom to show up on my first monitor, so which is like up above me. So kind of annoying. I try to use other stuff if I can.
You could be using Blue Jeans.
It works better for me.
Oh, see, there you go.
I usually use Meet.
Ah, yes.
So I'll just mention to everyone that Peter Michael is our session chair for this session. So I'll let you take it away whenever you're ready.
All right. You want to start right at 1, you think? Give people another bit or so? Or do you want to just go?
Yeah, we can give people another minute.
All right.
We have, like in the previous session, we've got an extra 20 minutes in this session. So actually, if you want to tell the speakers, like if everybody had an extra 5 minutes for your talk, that would be okay. We wouldn't go over our session time.
All right. Hey, speakers. Did you hear that? Yeah. So yeah, everyone's slotted for 15 plus 5, presumably. But if we go a little bit over on everyone, that's fine. So we'll let it. We'll play it by ear. So I think that's good. Okay, I think we're probably good. We can get started for this part. Hey everyone, if you're just joining us, welcome back to Hatcher 2020. I'm Peter Michael Acera, assistant professor at Grinnell College, and this is the types session for the workshop, i.e. the Rust and or what you call it, units of measure session. So we have a couple of talks about Rust and some stuff about units of measure. I'm really looking forward to this. So our first talk is by Will. He's at Stanford. I'll let him introduce himself. Take it away, Will.
All right. Thanks, Peter Michael. Give me just a second to share my screen.
Does Amazon use?
All right. Can everybody see my screen?
Yes.
All right. So great. Hey, everyone. My name is Will Creighton. I'm a 5th-year PhD student at Stanford, advised by Pat Hanrahan. And today, I'd like to talk about Rust, ownership, and the dark side of soundness. So just to give some brief motivation before I dive in, I have a decent amount of experience teaching functional programming languages to students. So I taught Stanford's course on programming languages where we use Rust and OCaml. I TA'd a few courses at CMU where we use standard ML. So I've seen my share of distraught students battling with these languages. And so my question, I was wondering, what have I seen that no one really talks about? So the first answer that came to mind was type inference errors, obviously. I mean, these are super tricky, they're really hard to interpret. So I got all excited. I was going to write my paper. And I was like, hold on, wait a minute. I'm an academic. I got to check the related work. And it turns out this is a really saturated field. A lot of people have strong opinions about how to interpret type errors or how to make better tools for them. So I was like, okay, next, let's keep moving on. I returned to a problem I had observed in a project a few years back with a colleague of mine, Anna Zhang. We had read through dozens of blog posts about people's experiences learning Rust. And one common theme was this, what I'll call a usability cliff with ownership. So someone would try to do something perfectly normal in another language. So like here, they were trying to mutably partition an array. So take a pivot and get 2 subslices with mutable access to both. Now, this would be totally fine in C++, but in Rust, it simply wouldn't type check. The author had no idea how to fix it, and they couldn't implement their program. And so this talk is a deep dive into this problem, or at least what it represents. And I think it illuminates an important usability issue in Rust, but also in type systems more generally, which is soundness versus completeness. So to explain more, let me dive into a few live coding examples. All right. Let's get my Emacs up. Let's make a new Rust file. All right. So I'm going to walk you through just the basics of what ownership looks like in Rust to get a sense of why it's useful and what kind of problems we might see with this. So in Rust, I can make a little vector. So let me say let mut v is equal to vec1, 2, 3. And then let me show you an example of how Rust comes in handy. If I try to write the following program, let x equals and v0, take an immutable pointer to the first element of v, then try to mutate v, so add 1 to the end. Then assert that the dereference of x is equal to 1. If we try and, let me turn off fly check mode. If we try and run this program, then we will get the following error. cannot borrow v as mutable because it is also borrowed as immutable. And so this is an objective win for Rust. This is an iterator invalidation scenario, which you could totally have in C++, because the dot push here might actually, because this is a resizable array, it could reallocate all of our elements, move them elsewhere, delete the original value, and now this x would be a dangling pointer. And so the way that Rust catches this is it recognizes this immutable, mutable conflict. And more generally, there's three main rules to ownership that are worth knowing. So the first is that all values have exactly one owner. The second is that a reference to a value cannot outlive its owner. And the third is that a value can have either one mutable reference or multiple immutable references. And generally speaking, if you see a program that doesn't pass Rust's borrow checker, you can look to one of these three rules to try and explain it. So here, the third rule is the one that's being violated. There's both a mutable and immutable borrow to the vector v, and hence it gets flagged as an error. And just as a quick example of the second rule, if we do this, we say like let x equals make the vector, return a pointer to v0, but then what happens here is v gets deallocated at the end of the scope. And so this is a dangling pointer to an element of v. And if we try and compile this, we'll get error v does not live long enough. So this is a violation of the second rule. So this is sort of the good side of Rust, which is using these high-level ownership rules, we can understand why basic patterns like these would be memory unsafe. Now let me show you a slightly different example. So let's say we have a vector and we want two mutable pointers into that vector. So x equals v0, y is v0. Then we'll say star x plus equals 1, star y plus equals star x, something like that. So this, we should expect, will also refuse to compile. It'll say cannot borrow v as mutable more than once at a time, a violation of the third rule because we have two mutable borrows, in this case to the same element. So absolutely wrong. We violated our ownership rules. But if we change this, if I make this v1 instead of v0, this program satisfies all three of those rules. These two elements, these two indices are guaranteed not to be the same. However, when I compile this, Rust still says an error. Cannot borrow v as mutable more than once at a time. So this is an example of a completeness issue, not a soundness issue. And you can kind of guess the reason is that Rust doesn't try and reason about the independence of array indexes. It would have to, because that would be a very general problem for any arbitrary symbolic expression. Could the two indices be the same? And they don't try and do that. That's a much more powerful logic that Rust is not going to try to have. But that means now we have two very different kinds of errors we can make, ones that are genuinely bad and ones that aren't bad, but Rust just doesn't let us do. And as another quick example of what that looks like, if I try to do something like v.getMute v0, so this gets me mutable access to the index I, where I is equal to v of 0, and I try to compile this, I'll also get cannot borrow v as immutable because it is also borrowed as mutable. This is a sound program. We're reading from the vector before we write to it, but Rust gets confused for whatever reason in the implementation of its borrow checker. And so that's my high-level point, is that these are examples of completeness versus soundness issues. Let me return to the slides. All right. And so the point is that this situation can happen a lot. You have a program with an ownership error, you've hit the borrow checker, but now what? How are you supposed to fix it? And so in the rest of this talk, I'm going to walk through my own process in diagnosing these errors. And along the way, I'll highlight the necessary skills that one needs in order to make a correct diagnosis, and how we don't always teach programmers about these skills. So the first question that I ask is my program unsound with respect to the rules of ownership? So we saw these two programs. Neither passes the Rust compiler, but the left one is sound and the right one is not. The way we deduced that was by using the rules of ownership. And more precisely, you have to look at each program and reason about whether each line could violate any possible rule. And you can imagine if we had like a formalized semantics, you could write a proof for a counterexample for both programs in a sufficiently powerful logic, but Rust doesn't have that in the compiler. And so the skill here is that we have to teach programmers to reason through these principles independently and to recognize in the first place that an issue might just be incompleteness and not soundness. And that might sound obvious at first glance, but my sense is it actually isn't that obvious to most programmers. With these weird, complex type systems like Rust, most people just learn to submit to the compiler. Borrow checker is always right in their mind. I showed a draft of my Hatcher paper to some acquaintances, and I was struck by how several people specifically mentioned, it was interesting that they didn't recognize that incompleteness could be a source of their errors before. So I think this is something that people may not know, but we should totally bring up to them. But let's say you've diagnosed your issue as a completeness problem. You know your program is sound, but it's just a matter of convincing the compiler. So then you can try and shuffle your code around to avoid these restrictions. So in the get mute example I showed, you can actually just bind v0 to a temporary, and this will work 100%. That's all you need to do. Here's a slightly more interesting example. So let's say we have a point struct with two fields, x and y. We have a helper function that returns a pointer to the x field. And then we have another function that mutates the point to set y to x. And then it has this extra assertion at the bottom. So this left program doesn't compile. And the reason is that the borrow checker loses information across procedure boundaries. So it forgets that get x is borrowing just x, and it assumes that it borrows the entire struct. And so to solve this, we actually have to inline the getX function. We have to directly put the ampersand into set y to x. And then our program will type check, because within that local context, the borrow checker can reason about the independence of the borrows on x and y. And so, this is not that great because we were prevented from defining the abstractions we wanted through procedures. We would have to use a macro if we wanted to get the same thing. And so this next skill is that you have to understand and plan around the borrow checker's limitations. You have to get the mechanics of that gap between what's logically sound and what's checkable. And then you turn that understanding into a program refactor. And so let's say that doesn't work. No amount of shuffling does the job. Next up is maybe there's a library function that can help. So in our disjoint indexing example, there's actually a vector function in the standard library that does exactly what we need, split at mute. So it partitions at an index, and it gives us mutable access to each partition. And you may wonder, how is split at mute defined? And the answer is unsafe code, but I'll wait for that on the next slide. Just as another example, if you're using an option and you want to get a reference to a value inside. So here you have a string inside of an option. You want to get a substring of that as a pointer through this name.get thing. This program will actually not compile because you try and take ownership of that string. And the trick you have to know as a Rust programmer is you need to do .as_ref. That takes an option of string to an option of pointer to string, and that's sufficient to make this code work without taking ownership. And again, the point is just that a programmer has to be aware of these functions. They have to know about them, they have to be able to use them, and part of gaining expertise in Rust is learning about these helpers so you can expand your set of checkable programs. And then finally, when all else fails, you have to use unsafe. So unsafe in Rust is designed for cases when ownership doesn't cut it. Usually this is for FFI, foreign function interfaces. But there are situations like split at mute where it's unavoidable due to incompleteness. And so the unsafe, by the way, is the little porcupine crab in the diagram. And so I can talk about my opinions on unsafe, but again, it turns out a lot of people beat me to the punch. Just this year, 3 papers were published at PLDI, ICSI, and OOPSLA specifically about the usage and dangers of unsafe in Rust. Everyone is very concerned. And so just a quick slice of what they found. About a quarter of published Rust packages contain some kind of unsafe code. Most people aren't using unsafe spuriously. A manual review claims that they're doing it for good or unavoidable reasons. And according to a small Reddit survey, these reasons are usually for performance or borrow checker restrictions. And so the main point is that to take away about unsafe is that it's easy to get wrong. The PLDI paper pointed out dozens of bugs where programs incorrectly designed their interfaces and then allowed memory safety issues to happen. So for example, here is a dangling pointer pattern. So you have a data structure with a pop and a peek method. You might peek, that's line 5, get a pointer to an element, and then you could pop it. Normally, this sequence would cause a mutable-immutable conflict, like we saw with the vector example. But this API forgot to make pop a mutating method. Now, normally you can't just forget to do that, but unsafe allows you to. And so if a programmer has to write unsafe, they both need to reason about the dialect of Rust for unsafe code, and they have to carefully design their interfaces to avoid issues like dangling pointers. So that is my patented process for debugging ownership errors. Hopefully I've convinced you that it can be a lot of work. And totally bewildering, by the way, for a novice Rust user. And so I have 2 main calls to action. The first is that we should make users of advanced type systems more aware of the soundness versus completeness trade-off. And then second, we need to think through the actual process by which someone goes about making this distinction, and then develop resources targeted at each skill necessary. So that's all I have to say about the usability of ownership. Thank you very much.
Yay, thanks, Will. I'll clap. Other people will clap too, undoubtedly.
Thank you.
You're welcome. All right, so I mentioned in chat, if you have a question, could you, rather than raising your hand, because I can't see everyone's faces, can you please type in a Q in the chat so that I know you have a question? I'll call on you from there. Jonathan Aldrich points out that there is indeed a race condition. He is correct. I would love for you to exercise the race condition by having tons of questions. So do it. All right, so first question, Vishnu, go ahead.
Hi, Will. I was just wondering how much of these usability issues of incompleteness in Rust BioChecker do you think could be solved by just having the documentation be more clear and transparent about this limitation? Because it seems like right now, the Rust documentation just seems to hide this fact.
Yeah, so definitely, I think telling people about this issue and having them, well, you know, the first thing is to raise awareness. So people should recognize that incompleteness exists. The second is to have people exercise that muscle of doing ownership-based reasoning on their own without the help of the compiler. Most people I know who use Rust, they just assume if it tells you to put in an ampersand, they're going to do it, right? But that also doesn't solve issues like number 3, where knowing where to find and how to find these library functions can be quite tricky. Like, what is the type signature I'm looking for? What is a relevant library? You know, split it mute is one example, but there's also dozens of others that I've seen in my experience, like take mute, where you have a mutable reference, which you temporarily turned into an owned value and then turn back into a mutable reference. So there's like a lot of different small patterns I've seen. And you know, like one basic thing might just be an index of those, some sort of resource that compiles together all of these like intermediate level Rust hacks, I think would also be valuable.
Excellent. Michael, go ahead.
So thanks for the talk. It was really interesting. I wonder, you know, Rust elevates mutability to a really central role in the type system. And I have worked on mutability some, and it's interesting to me that the kind of mutability that Rust expresses is shallow, right? So, and this is, it's expected that there may be interior mutability, and that fact is not expressed in the type system at all, right? So you can have an immutable value, which actually on the inside is mutable. And so I guess I wonder a little bit whether Rust is really providing the right guarantee, right? You talked about the Rust guarantee. There's only one mutating reference to an object or to a value at a time. But actually that's not true if there's interior mutability, right? You can have many immutable references to the value where actually they're all mutable. And so if you want to have ensure safety in that sort of context, let's say for concurrency, then you need additional mechanisms. You need to think very carefully before you make something sink or send. Can you talk a little bit about what your experience is with that? Do you think Rust did the right thing? Do you think Rust did the wrong thing? And if so, what should it do instead?
I mean, I think Rust did the reasonable thing. Like, it still is a nice, to me, idea, which is you capture interior mutability in as small of an API surface as possible. And then once you're outside, like, for example, you have an arc of a lock, right? And once you've copied your atomic data and then you've locked it, you now have like a normal mutable pointer which adheres to all Rust rules, and you can't like mess that up in any way. It's only if if you do something fudgy with the interface, or in particular if the implementers of the mutex data type did it wrong, then you're going to have a bad time. But in general, my sense is most interior mutability is encapsulated in a relatively small number of interfaces that once we get bulletproof, which I would say for all intents and purposes they are in Rust, you don't really need to worry about it. I mean, I think that to me, the deeper issue is that interior mutability makes it harder to form a coherent mental model of how Rust works. So when you have an arc of T and then you call x.clone, you're like, oh, it copies the data, of course, right? Well, no, it gets a new reference to the data, the exact same data, right? You're like, well, and that completely wipes away what you thought .clone did. And so I think there's a number of issues like that where it's just, these are surprising to people learning the language. I mean, eventually you get it once you have the appropriate schema in your head for like why this design is good and alternative designs would be worse. But I think it takes that level of expertise to get really comfortable with these APIs. So, I think they've done the best with what they could, and I'm pretty satisfied with it. But I think from a learning perspective, it makes it challenging to form that mental model about like what each operation is going to do literally at runtime. Getting the notional machine in a way.
So some barriers can be. Well, I'll give Gabriel a go because you have another question, then we'll come back if we have more time. Thank you.
Gabriel, go ahead, and then Michael's back on deck.
Mine is just a short question. So this is definitely a trade-off between like managed memory, right? Like managed memory is also memory safe, but it's a lot easier to use. So who, like, these skills are definitely useful, but I'm wondering who do you think the target population of Rust is, and how does that involve the skill, right? Like I'm assuming that maybe not everybody that goes through a computer science program should learn this, or maybe everybody. Like what are your thoughts on who are the target population and how can we get them the skills?
I mean, I'm an extremist. I think anybody who's doing systems programming, if you refuse to have a garbage collector, and there are a lot of people for good reasons who don't have garbage collection, game programming, embedded programming, so any kind of systems programming, right? There's lots of good reasons why we don't have garbage collectors, and anyone who does not have one should use Rust or something like Rust. I mean, I think at this point, it is just patently irresponsible to use C or C++, given particularly for security or mission critical applications, right? If it's your like random data pipeline, whatever, but there's so many, like Microsoft has a blog post that's like 70% of errors every year are just memory safety things, buffer overflows and stuff like that. And so it just makes really good sense to have a language which strongly protects against all of those things. I think it's more like, if you are going to allow yourself to work in a world, like it's like an ethical responsibility thing, like an engineer's sort of code. If you want to go off and do like high level garbage collected stuff, that's fine, go do that, right? But if you want to write production level systems code that you're going to give to people, you should write it using a language which is going to make sure you don't put in these dumb memory safety issues or leak their information or whatever. So I'm pretty strongly in favor of this for people who need to do systems programming.
Can I do a follow-up, or do we not have time?
Oh, you're good. Go for it.
So you mentioned game developers, right? In the gaming industry, you care a lot about speed, right? Because you have to get the game out as quickly as possible. But you don't is it really that bad if it crashes on a memory bug? Like I'm not aware of any like critical issues. So like that's what I'm saying, like regarding these trade-offs, right? I'm not entirely sure that this is something like most people that graduate from computer science degree don't necessarily go to write the next leap C, right? So where do you think we should teach these skills?
Yeah, so I mean, game development is definitely one thing where it's like less mission critical. It's more like a user experience thing if your game crashes in the middle. I mean, to me, the other deep issue is that of a community. Like and I've made this argument before, but when you have something like a strong type system to prevent memory safety, a big issue in C++ is it's very hard to import other people's code. And when you do, you have to be very skeptical about it. You're like, I have to make sure I'm using it in the right order and I don't mess up their invariants and whatever. And a type system / language that makes it easier for people to share their code in a safe way, promotes a healthier ecosystem. I can feel less concerned to just pull in random people's packages and try and run them. Than if I, go into C++ mode. So I think even for casual applications, having a strong type system can be a great benefit to reducing the sort of barrier to entry for adopting other people's code.
Thank you.
Yeah.
Excellent. I think, Michael, you want to ask that last question real quick?
Yeah, thanks. So on the one hand, intuitively, I agree with you. Rust seems like basically the right thing. On the other hand, if we think about this, let's say in a disconnected scientific way, right, it seems like we should be able to produce empirical evidence for our recommendations, right? So if we want to say software engineers will overall be more effective at writing the kinds of software they want to write if they use Rust and not C, which seems like a reasonably good hypothesis, right? Then we should be able to show that that's true in some sort of empirical evaluation. And so I guess my challenge for the community then is figure out how to do that in a way that people believe in and then actually do it, right? So, you know, is the economic trade-off worth it in the context of games? Well, if we can figure out what the trade-off is, maybe we can try to quantify that.
Yeah, I think it's a totally good point. I've talked to people who worked at Twitter who said they felt the decision to move from Java to Scala was really bad because it took way more effort to learn Scala than it was worth in productivity. So, you know, that I think this is an interesting question to look at. To me, the memory safety bug statistics are like the easiest point of evidence to point to. There are metrics out in the world that justify through experience why writing in a certain way can be problematic. But I think there can definitely be a lot more done. And you know, Sarah's in the call. It's funny. I'm taking her class, and we were just talking about how what are the different reasons one would justify programming language adoption. So I think there's a lot of different ways which we could go about this.
I mean, sometimes you make something safer by changing it so that it's safe, and other times you make it safer by adding warning labels.
That's true.
Right? Warrant caution ceiling low, duck here. You know, like we still have those signs, even though the solution is raise the ceiling, but that's very expensive.
Yeah. But the issue with the warning label, right, is just that, and I go back to the community thing, you can't trust other people to not duck, right? Like I want to make sure that other people didn't, you know, set up their environment in a way that I'm going to shoot myself in the foot. And I think that trust issue is one that's hard to quantify, but to me, being in the Rust community for a while, a very important aspect of why it's so easy for people to share code.
All right, cool.
Thanks.
Let's thank Will. I guess
everyone.
I'm clapping. There we go. All right. Next up, I think Gabriel, you're going, right? Is it?
It would be. Sorry, it would be me. It'd be me. Sorry.
Okay, yeah. Not Gabe, who just was in the Q&A. That would be surprising if you had to give a talk all of a sudden. But yeah.
Yeah. Can you see my screen?
All right, we'll let Gabriel set up real quick. Gabriel's going to be talking to us about RustViz, a visualizer for ownership and borrowing in Rust.
Can you see my screen?
I can see your screen.
Okay. By the way, I'm Vishnu.
Oh no, you're Vishnu. Okay, sorry about that. My bad.
Yeah, no worries.
I was trying to go off the participant list, but yeah, go ahead and take away when you're ready.
Hi folks, my name is Vishnu and I'm part of a team of undergrads along with Professor Cyrus Omar in the Future of Programming Lab at the University of Michigan. And we're working on RustViz, which is a tool we're developing for interactively visualizing ownership and borrowing in Rust. And I'd also like to give a special shout out to Jason Zhang, whose help with developing RustViz has been quite valuable. So I'm going to give a brief overview on Rust, and hopefully you guys also got a good background from the previous talk as well. Most popular programming languages use one of two strategies for deallocating memory allocated on the heap. The first strategy is to have the programmer responsible for explicitly deallocating memory, and this is what C and C++ does. And the advantage here is we don't have to incur the performance cost of garbage collection. However, this could lead to issues like use after free bugs, double free bugs, or memory leaks, which are all very nasty to deal with. And the other strategy is to use a garbage collector to free memory, which is what most other popular programming languages do. And this avoids memory safety issues, but incurs a performance cost. Rust is different in that it has memory safety without needing a heavy runtime system. So instead, it uses rules based on ownership and borrowing, which are enforced at compile time by something called the borrow checker. And the advantage here is we have memory safety without the performance overhead of garbage collection, which is great news for performance critical applications. And I'll talk more about these rules in the demo. Now, there's a trade-off here, which is that these ownership and borrowing rules make Rust more stringent than what most programmers coming from other languages are accustomed to. And this can present usability issues for new Rust programmers. Because of these unique rules, Rust learners have to develop new mental models. And because of the stringency, many patterns that work in other popular programming languages will not pass Rust borrow checker. And the difficulty of learning Rust, even for experienced programmers, becomes apparent when going on online forums and seeing a number of posts where Rust users hang out and seeing frequent complaints of fighting the borrow checker. So these difficulties that Rust learners face is our motivation for developing RustViz, which is our tool for generating visualizations of ownership and borrowing in Rust code, given memory events that are determined in advance by the person creating the visualization. So I'm going to show you guys a couple of examples of these visualizations and explain an approximation of Rust ownership and borrowing rules along the way. So on the left-hand side, we have some example code. And on the right-hand side, we have timelines of ownership and borrowing events. We have a timeline for each variable. So in this example, we have a timeline for S, X, and Y. And in the timeline, we have these dots and these arrows, which are aligned vertically to where these different events happen in the source code. And as you can see, there are messages that appear that explain what's going on as you hover over various elements in the visualization. So figure 1 demonstrates these rules in Rust. Every resource has a unique owner. Ownership can be moved, and a resource is dropped or deallocated when its owner dies. And so I'm going to go through line by line and explain what's going on in this Rust code with the help of the visualization. So on line 2, the function string from, which is represented by this F icon, creates a heap allocated string, and it moves ownership of that string to S. The move is represented by this arrow, and S acquiring ownership of that string is represented by this dot. Since we didn't mark S as a mutable variable, this line segment here is hollow, and the hover message says that the binding cannot be reassigned. On line 3, the function takes ownership is called with S as a parameter, and this causes ownership of the string resource to be moved into the function. And so at this point, S no longer owns a resource and it's no longer valid for use. And that's why the line segment in S's timeline ends after this call to takes ownership. And so for a developer coming from other languages, they might expect that the string would get copied or a reference to the strings taken. So this is a bit different than what most Rust learners would be used to. On line 4, we introduce a mutable variable x and bind the integer value 5 to it. Since we marked x as a mutable variable, the line segment here is solid as opposed to hollow for s. And the hover message here says that the binding can be reassigned. And then on line 5, we introduce the variable y and initialize it with x's value. In Rust, types with stack-only data, like integers, generally get copied with some exceptions. So what's happening here is x's value is copied to y rather than moved, which the hover message on the arrow explains. And since this was a copy rather than a move, x is still valid for use at this point. And the line segment in x's timeline continues alongside with the line segment in y's timeline. On line 6, we assign the value 6 to x, which is allowed because x is a mutable variable, and this is represented in the visualization with this dot. And then finally, on line 7, we reach the end of the function, and all 3 variables go out of scope. Since s doesn't own a resource at this point, it going out of scope does not cause a drop, which the hover message explains. Now, if we didn't have this move of s's resource that takes ownership, and s still owned a resource, then at this point, when s goes out of scope, the resource would have been dropped there. But since it was moved, it got dropped somewhere else. X and Y still own their integer value, so the hover message says that its resource is dropped for X and Y, though this isn't really that interesting since these aren't resources allocated on the heap. Figure 2 demonstrates these rules in Rust. Borrowing allows us to use a resource without taking ownership. We can mutate resources through mutable borrows, but not through immutable borrows. We can have multiple immutable borrows live, but if a mutable borrow is live, it is the unique borrow. And so what that means is we can't have any other mutable borrows or any immutable borrows. And again, I'm going to go through this example line by line and explain what's happening. So as with the previous example, we create a heap allocated string and move ownership to S. This time S is a mutable variable. And on lines 4 and 5, we have R1 and R2 taking immutable borrows of S. The dot for S says that its resource is immutably borrowed. The arrow says there is immutable borrow from S to R1. And the dot on R1 says that it immutably borrows a resource. And we see something similar on line 5 for R2. And so when we take these borrows, the timeline for S is still there because S still has ownership of the resource and it's valid for use. Something that's different about the timelines for R1 and R2 is this curved line to the side. And for variables of reference type, we add this line to express the kind of borrow that's happening. So in this case, we have immutable borrows, which is represented by a dashed line. And when I hover over it, I can see the message, cannot mutate star R1. The star here is the dereference operator. So the message is saying that we can't mutate the resource that R1 is referring to through that reference. On line 6, we pass our references to the function compare strings, which is denoted by the dot with the F on it. And since this is the last use of the reference, the borrow is no longer live after this point, and the borrow is returned, which is denoted by the arrow going back to S and the line segments in R1 and R2's timeline ending. On line 8, we have R3 taking a mutable borrow of S. Since this is a mutable borrow, we have a solid line to the side here, rather than a dashed line for the immutable borrows above. And we also see a gap in S's timeline. And that's because when a mutable borrow is live, the owner can't access the resource. So, and as we said earlier, we can't have a mutable borrow live when other borrowers are live. So how come this doesn't conflict with R1 and R2? This works due to a feature in Rust called non-lexical lifetimes, which makes it to where references are no longer considered for conflicts after they're no longer live. So in this case, the last use of R1 and R2 were for this call to compare strings. And so afterward, the references are no longer live and they don't conflict with having the mutable borrow for R3. And then in line 9, we pass R3 to the function clearString, which means that clearString can mutate the resource, and then the borrow is returned back to S. Now, as we speak, we're actually trying this out on around 70 upper-level undergraduate students in a programming languages course. We wrote up a tutorial on Rust ownership and borrowing system and included these visualizations in there to aid our explanations. And then after the reading, we have the students answer questions that test their knowledge on ownership and borrowing, like this one, which has a Rust code example, and the students have to figure out where a resource is dropped. Now, since this is part of an assignment that we're giving students, we can't do a controlled study like we proposed in the paper. However, we hope to get good qualitative feedback, and perhaps we can see how students this semester seem to grasp Rust as compared to the previous semester where they didn't have any visualizations to help their learning. So the next step for us is to conduct additional studies. We would like to conduct a controlled study like we proposed in the paper, but it would also be useful to do more pilots in the classroom setting. So if anyone is teaching Rust and is interested in collaborating here, please shoot us an email. We'd also like to make some tweaks and additions to the visual design. In particular, it'd be nice to come up with ways to elegantly visualize code with borrow checker errors to help explain what's wrong with a certain piece of code, or elegantly visualize branching and looping constructs, which we currently didn't put much thought into. Another thing is making improvements to the workflow of generating visualizations. Currently, the workflow for creating visualizations by describing the events using our Rust library that we made is admittedly tedious. So it'd be nice to make this simpler. And we may even look into creating a simplified domain-specific language for creating these visualizations as an alternative to using our Rust library, which might have good improvements to the ease of creating these visualizations. Another avenue of exploration would be automatic generation of the visualizations from source code. We're not entirely sure of the viability of that, though, because the visualization might not scale up well in larger, more complex code examples. And also the model of ownership and borrowing that we present in the visualization is more simplified than what's actually happening under the hood. So automatic generation might make the visualizations too complicated to be pedagogically useful. There has been some other work done on visualizing ownership and borrowing in Rust, mostly in the form of blog posts and online forum threads with different mockups of ideas. This blog post by Phil Ruffwind presents a mockup of an idea for visualizing ownership and borrowing. It uses a vertical timeline similar to our approach. And this post was actually one of the inspirations we had as we were thinking about how to design our interactive version of visualization. And then on the Rust internals forum, there's this really long thread started by Paul Daniel Faria with ideas for using visualization from RLS, which is a language server for Rust, to visualize borrows inside an editor. And so this thread contains a number of mockups and ideas, but one cool thing was that Faria was able to accomplish getting a prototype working in Atom. And this code can be found on GitHub, but it doesn't seem like there's been much work on this recently, and it seems like the project has been somewhat abandoned. This blog post by Jeff Walker was inspired by that prototype that Faria created, and they made a mock-up of how this information could be better shown in an editor without having to highlight entire lines of code like Faria's prototype did. There are also a couple of bachelor's theses from ETH Zurich. The first one is by Dietler Dominic, and they identify lifetime constraints and generate a directed graph visualization based on these constraints. And then the second one is by David Blazer, and they build on Dominic's work by creating a system for explaining errors in VS Code and including a graph-based visualization. So thanks for listening to my talk about RustViz. If you want to take a look at the project on GitHub, here's the URL, but keep in mind that we're still actively developing it, so there are going to be changes in the coming months and weeks. So now I'm going to open it up for questions.
All right, thanks, Vishu. And everyone else is clapping too, I guarantee it. All right, so if you have questions, queue in the chat. We got, oh, looks like Justin up, Michael on deck, and then I forget my baseball analogies from there, but we got a lot of questions. So Justin, take it away.
Thank you. Yeah, and thank you for the talk. That was really great. I was curious if you've thought of any way to visualize basically like incorrect programs, or where the borrow checker would say that it is not sound, because that would be sort of interesting pedagogically too.
So yeah, as I touched on earlier, that that's one thing we haven't thought of that would be interesting, would be visualizing code with borrow checker errors. We haven't really thought about visualizing errors due to unsound or like incompleteness in the borrow checker. I think that would be my initial thought there would be difficult to sort of convey that to like very beginner Rust learners who are just only have experience with like C or C++, which is what the University of Michigan uses in our computer science curriculum to this. I feel like that would be somewhat of a jump for a first introduction, but it would be interesting to think about.
Thanks. Yeah.
Excellent. Michael, you're next.
Thanks. Great talk. I wonder if you could talk a little bit about the sort of the design process for this. In particular, I think you had a choice between what you did, which is sort of showing the whole story as the program is executed, versus showing it more like a video where you have individual snapshots of here's the ownership situation right now for any given program point. Can you talk about that trade-off or other trade-offs you considered?
So we never actually had, that's an interesting thought. We didn't think about like showing it sort of as a video of like these things that are happening like in a chronological sense. I guess my first thought there is like, it sort of tries to present a concept that happens statically as like a runtime sort of thing. So I don't know if that would be pedagogically as useful as showing the entire snapshot, but yeah, we haven't actually thought about showing it that way.
Okay, thank you.
Excellent. Will, go ahead.
Yeah, this is really cool. I read through your learning goals, and they very much resonated with me because when I teach people, for example, like someone mentioned in the chat, how ad hocness in the system makes it challenging to learn. When there's all these exceptions to the rules, you kind of miss stuff. And I think Rust borrow ownership can have a lot of things like that. Like move versus copy is initially a very ad hoc thing. You're like, oh, why does this not work on strings, but it works on integers? And you get really confused and frustrated, right? And it's that sort of root cause analysis that's really tricky. So I guess I was trying to think about more broadly, like, would you use this more as a learning tool or as a debugging tool, right? And I assume the answer is somewhat both, but it might need to be tailored to different contexts. So like, for example, if you use this as a teaching tool, I think it would be cool to have someone try and draw the diagram themselves and then to compare that against the actual diagram, right? And have people engage in this constructive process where you can use this as like a check your work thing. And I'm curious if you all have come up with other ideas in where you would specialize this kind of diagram to either context.
So going to your point about using it as debugging tool, I think in order for that to really be that useful, we got to start pursuing automatic generation, which right now it's more of a process of the person creating the visualization like gives as input the memory events in Rust that occur, and then the tool gives you the visualization. So the tool right now is designed more as a teaching tool. And I touched on like maybe some of the challenges that might happen from automatic generation of the visualization. So I think that would be difficult, challenging, but that would be a difficult challenge, but it would be interesting to see how it could help debugging. But yeah, for now, it's mostly intended to be used as a teaching tool. And we have actually put some thought into maybe having some exercises where students try to draw out the visualization on their own, but we haven't actually tried that out with students yet.
Excellent. Alan, go ahead with your question.
Yeah, it was a really nice talk. So the examples that you showed here were all for stack allocated data. I was just wondering if you knew what the heap allocated version would be.
So this is a heap allocated string. The uppercase S is a heap allocated string. So we showed the behavior with heap allocated data types here.
Yeah, but you're not actually visualizing the string itself. I mean, the stuff that's being visualized is the stack allocation.
Oh, I see what you mean. So we are visualizing the ownership and borrowing aspect of it. So we're showing like what variable owns certain things. So like what variable is borrowing a certain resource. We're not. That's really the what we're trying to teach the students, because in terms of like how things are allocated on the heap and stuff like that. I guess I think the audience that we're targeting sort of already has an understanding of that. Like the upper level students in computer science at the University of Michigan are familiar with this through their experience with implementing dynamically allocated data structures in C++ in their computer science curriculum. And then if we're talking about other experienced programmers coming from other programming languages and wanting to use Rust, we would think that they also have like an understanding of how things resources would be allocated.
So you're not hitting issues where people are using things like interior mutability. So the APIs for complicated lifetimes on the heap, they're not hitting them.
No, this is supposed to be for beginner Rust programmers, so we're not really touching on anything like more like at this point we aren't even like touching really like things that are considered intermediate sort of Rust concepts. We're doing like really basic things just to give people an introduction to the ideas of ownership and borrowing.
Excellent. And I have one question. You're doing the study right now, right? With the kids in the class? Like
yeah.
right now?
Well, it's not a controlled study, obviously, because it's a classroom setting, so we have to give everyone the same thing. But hopefully, we'll get like some good qualitative feedback on that.
Do you have any preliminary findings you've seen, or any sort of initial reactions from students that you've encountered so far?
No, not particularly. I mean, like we just released this. Like we released it on Saturday, and the students are still working on their assignments. So hopefully, after the assignments due, we'll get some useful information there.
Excellent. Cool. All right. Let's thank Vishnu one more time. I'll do it.
Thanks.
Sweet. Excellent job. All right. Dominic, you there?
Yep.
Oh, good. Okay. that little delay just threw me a little bit off kilter. Hopefully the kids are doing well.
Yeah, everyone's asleep.
Excellent. All right. So yeah, Dominic's gonna finish off the session by talking about units of measure. So go ahead and set up, and when you're ready, take it away, sir.
All right, all good with the setup? Can see everything?
Yes, I think yes, this is good.
Excellent. So thanks very much, and thanks to my collaborators, Mistral, Matt, and Andy. So some number of years ago now, Andy and I found ourselves having conversations with scientists over lunch, and we kind of realized that in the sciences now, like a big part of doing modern science is writing code, is programming, and a lot of in lots of areas of science, the only way in which models are the main way in which models are expressed now is actually via complex programs. And we're having these chats and we're saying, oh, this is really interesting. You know, you spend all your day programming. We're PL people, and we have lots of ideas about how we can make programming better. Would you be interested in having a chat? And you know, maybe we could help you out with some of the things you're doing. And they're like, oh, yes, please, that would be great. And since I'm sort of like a verification-y kind of person, I was saying like, oh, well, how do you know that your software is correct? What do you do to sort of ensure that it's doing what you think it's doing, that the models behave in the right way? And they're saying, well, we are interested in that. We do various kinds of testing and so on. And we talked about how, oh, well, there's loads of really cool stuff going on in our field. Like we were developing loads of verification tools, and they're like, oh, yeah, that sounds great. And so then we're like, oh, yeah, we've got all this stuff. We've got these like theorem provers and these analysis tools. And they're a bit like, okay, we don't understand any of that. So many years ago, we decided to sort of start putting together a bit of a research program, a bit of a project, looking to try and cross the chasm between PL researchers and scientists and actually start having sort of meaningful conversations with them. And this, we also sort of observed that in the past, computer science and the natural sciences were very close. Like computer science almost developed as a service to science. And then over the years, like computer science and the sciences have gone apart. We've sort of developed and matured as our own field. Okay, there's still some crossover in the sort of HPC circles, but there's been a sort of divergence there. So Andy and I sort of came up with lots of ideas, and we started talking at these computational science conferences, and we built we wrote this paper about the challenges associated with verification in modern science after lots of discussions with scientists, and we sort of started proposing sort of programming language ideas and research agenda around PL for computational science. And I think in the end, basically a lot of what we felt like we were suggesting was sort of new programming languages and sort of thinking quite like far out ideas in PL that could help people write fast and efficient and correct scientific models from scratch. But then, you know, language adoption is really difficult. It's fraught with difficulties. It's very hard to, you know, we start thinking, well, we can't just make up a language, like no one's going to use it. You know, it takes a really long time and effort for people to use new things. And also, you know, there's not a good understanding of how to ensure adoption of languages either. So we sort of went back to the drawing board, and we started thinking, well, what we should do is start building tools instead that work with what people have now. Because a lot of the scientists we talked to are saying, well, we've been we have this model and we've been developing it for 20, 30 years in this lab, and we want to keep using that and developing it. So instead, we decided to start targeting popular languages in this domain. And since we were talking to mostly mostly climate scientists of varying kinds, this meant ye olde Fortran. And at first, I think I was perhaps a bit afraid of that. I feel like in PL circles, Fortran is a bit of a dirty word. But actually, modern Fortran can be really nice. And I've seen some exceptionally good code from people. Some quantum chemistry models in modern Fortran. I just think this is incredibly well engineered code. So it's, it's sort of modern Fortran has a lot of really nice stuff in it. It's a bit like a nicer version of C, right? C without pointer arithmetic, with first class arrays. Even has an effect system. You can mark things as pure that then get automatically data parallelized and all that kind of stuff. So we started building this project around the idea of kind of addressing legacy code and long-running projects built with Fortran. So we had sort of two prongs to this. One was about sort of evolution tools, refactoring tools, but the other was about verification, trying to build verification tools that scientists could use with their existing processes and could kind of easily adopt, and then it would just start helping them to sort of build confidence in what they were doing in their code. That's with these fine people and lots of interns and students over the years. And this was a project that was we had some government funding for that ran until about 2018. And then in 2018, Matt, our postdoc, I'm not sure if you can see my cursor actually, so I'm waving it around, but so Matt, he spent a year at the Met Office. The Met Office is like this government, part of the government that has thousands of people working for it. They have a really good climate model that's also used for small scale weather predictions as well. It's used by loads of governments around the world. Hundreds of scientists have been working on it for decades. They have loads of massive supercomputers. So they were interested in using our work. We built a tool that could do lots of things. It's kind of a Swiss Army knife. Well, no, I shouldn't say that. It's basically like a bunch of tools all together. And when Matt was there, they sort of said, "Oh, could we have this and could we have that?" And so our tool runs in their CI process now overnight, which is interesting. And Bloomberg have been using some of the libraries that we built to build their own tools there as well. So one of the things, the thing I'm going to focus on today is units of measure typing. This was something we hit on pretty early on when we're talking to scientists. We were we'd sit down in a room with these research groups, and they'd open up Emacs or Vim with their code, and we'd sit there just talking about the code. And we were saying, "Oh, look, in your comments, you have all these comments with units of measure in. Oh, that's really cool." And then one of the postdocs would be like, "Yeah, but they're wrong. Like that one's wrong. Come on, like I thought we changed that. That one's wrong." And, blah blah blah. And we said, well, units of measure is something that the PL community has thought about for a while. And Andrew Kennedy's work springs to mind. In the 90s, he really kind of studied and built the idea of units of measure as a type system in a sort of polymorphic ML style way. And we said, well, what if we built you a sort of external optional type system for Fortran that checked units of measure, and we could transfer your informal comments into formal specification comments. And they said, "Oh, that would be fantastic. That'd be really great. That'd be really useful to sort of have these things checked, especially in when we've got these 6 different models, and this one's 30 years old, and this one's 5 years old, and this is the rewrite of this one, and blah, 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 blah." So they were very interested in that idea. And so we set to work. We did a lot of thinking about what we thought a lot about the human aspects, which is why I proposed to give this talk. They were really interested in having something that integrated really well with their existing tools. It makes sense, their existing pipeline. They were a little bit concerned with it being moderately fast. We never worked out exactly what that meant though for them. But also the thing they're really concerned about is working with legacy code, working with the code they already have, which might be hundreds of thousands of lines or up to 1 million. So we realized we need to build something external. We need to use something that has specifications as comments, so they can use all the version control and use the compilers they use already, and use the weird refactoring tools and macro preprocessors they already use, and that will all be fine. And if we're going to if this is going to be adopted into existing projects, then there needs to be an incremental approach. You need to be able to do it to just parts of the system at a time, with inference and also guidance as well. So I'm going to give a demo of the Camfort's features here, a quick demo. We realized at the time there was an ISO standards proposal for adding units of measure typing to Fortran. And we've talked to the standards committee people about this, the person who's proposing it, and he's been trying for years to get it added to the Fortran standard, and it's never been approved. But we took some of his ideas and his syntax and said, well, let's do that, but use things like type inference and polymorphism and do a few other cool things. So I'm going to switch to just a quick demo. Here's a kind of just a Fortran program that I came up with. It's just a standard imperative code. I typed code. I defined some, well, these are floating point valued things. And then I have a function call here. This function is just for the purposes of this example, it does the square of its input and returns that. And then I stick a bunch of things together. So the thing that we realized like fairly early on, we started looking at code and we thought, well, if we want, the ISO proposal said, when you turn on this units of measure feature, what you need to do is give the type for every single variable in the program. And you need to give its unit for every single variable. And we thought, okay, how many variable declarations are there in this 100,000 line piece of code? Oh, there's about 10,000 variable declarations. So the user has to go and write 10,000 specs. A bit of a non-starter. So we thought, well, okay, they don't really need to write that many if we use type inference. They only need to put some key ones in and then everything else should be inferred. And then we thought, well, how do they know which ones to insert? So we built one of the things that Camfort does is it has this unit suggest mode, which basically runs the inference algorithm and looks at the constraints and when it's an under constrained system, does some sort of little heuristics to say it finds a minimal set of variables. We call them the critical set, a minimal set of variables for which if a specification is given to those, then we can solve the constraints of the whole system. So it's like you annotate these and then we can infer everything else. So in this example, it said, okay, well, give me T and X. So I write these comments in here. Let's say, this is meters or something. I don't need to declare the units. I can just put them in like that. Okay. So then I can run it in check mode. It's going to check these things. I can run it in inference mode, which will then tell me about the rest of the variables in the program. And that's the case. It was checking. It said everything was fine there. And then another feature we added is it's called the synth mode, which is like inference, but also generate all the specifications into the file. What's the flag there? Is it? There we go, in place. So it's running and it's doing the inference on the whole program. It's telling us about that there, but then revert my buffer. And what it's done is synthesize these specifications into the code. So down here, we see that this is a unit polymorphic function. We're using sort of ML style syntax to say, okay, the input is some unit alpha. So then the output is alpha squared. And then the applications of these things would get meter squared and second squared. So that's the kind of, there's these four modes essentially you can use it in. There's the suggest, infer, check, and synth. And we have a bunch of other verification approaches that are part of Camfort, and they tend to have these four modes: synth, infer, check, and suggest. So we had an OOPSLA paper a few years back about something to do with array computations and verification there. So, hello, come back. There we go. So I won't go into the details of how the critical variable analysis is done. I mean, the highlight is basically that we take code like this, we generate constraints about the unit. So the unit of A has to be equal to the unit of E here, and the unit of A has to be equal to the units of B times C times D. We do a log transform on this, which gives us linear equations. We then put it into a matrix and do essentially a form of Gaussian elimination to get reduced row echelon form. Actually, I think we use Hermite normal form. But then we can read off from this when we have gaps in the solution that tell us, oh, well, this thing is under constrained. If we knew C, then we'd be able to solve this for every variable. So that's roughly how it works. So in some earlier papers about this, what we tried to look at is how much of an effort saving is this? So if we take, we took a load of sort of small programs, and we looked at the size of the suggested variable set, the critical set, and divide that by the number of variable declarations overall, take that as the inverse ratio, and we found that the median, so that tells you like how many did you have to write, how many were you suggested to write versus if you had to annotate every single variable, and we found that the effort saving there was about 80%. We think that actually as the programs get bigger, it tends to be the improvement, the saving, it gets even higher. So that looked encouraging, like we could actually save people time here. So then there's questions about this, like how do we make this scale? How much of a weight is acceptable for people? So I'm not going to put loads of, we've done quite a bit of analysis, and we have lots of techniques for doing things like separate compilation versus whole program analysis. And one example, Cliff's, this is a seismology model. And that was about 40 seconds to do the entire project, but it's pretty small. It's only just under 3,000 physical lines of code. So 40 seconds didn't seem too bad for people. Scientists didn't seem too concerned about that if it was going to find them errors. You know, they don't need to run it every time they compile. They wouldn't really like that. But then when we go to the Met Office, that's like 1 million lines. So that's about 33 minutes if we take that as a benchmark, which might be fine in a CI build, but not when you're doing day-to-day programming. But then our approach does work at the module level. So you can do it like a little file at a time. And there the performance can be not too bad. Okay, so better wrap this up. So there's still a question. We haven't done the user studies. We would love to. It's just difficult to find the time and the resources to do that. And also, you know, what are the right metrics here? Do we look at how long it takes for people to write the specs? How many errors are found? Can we compare like errors found if you start with writing the specifications from scratch for a new piece of software versus adding them later? It's very hard to trial that when you're working on, you know, problems that tend to be in the order of tens to hundreds of thousands of lines of code. And then how do we get this out there to scientists? Well, we've been doing kind of training workshops with scientists around Europe for a little while. That's kind of cooled down now. We've been trying to raise awareness of this, but I still think we've got a long way to go in terms of making a tool that's sort of mature. And it's difficult because, you know, we're research scientists who are trying to publish PL papers the rest of the time. So it's difficult to get these results really, these things really usable out there. I was going to skip this. We have done a few studies where we've tried to find bugs in open source projects like the WRF climate model. We did find things that looked suspicious there. And whenever we talk to the people who own the code, they're basically like, oh yeah, that's fine because of this issue. But yes, it's not well documented, or there's like some complicated physics reason why it's okay for you to do this. So things like that, where they were sort of saying, yes, that looks weird, but you know, kind of things. Yeah, so I think I'm gonna end here. So the kind of transferable ideas that I thought were nice about this, the sort of human aspects, is this suggest mode, like guiding the user where to put annotations to maximize their information. I think this can be applied in other settings, other kind of qualifier systems and analysis systems. And also this idea of like automatically generating the specs. There are tools that do this for type qualifier approaches. And I kind of think like, why don't other typed programming languages do this? Like languages that have type inference, they could also do this. You could query the compiler and just be like, oh yeah, insert that type that you've inferred into my code, because that would be really useful documentation for my team later. So yeah, I encourage you to cross that chasm. You know, the future of humanity might depend on it. So I think it's good that we have these conversations with scientists. And I'll stop there. Thanks.
Sweet. Thanks, Tom. Yay. All right. Same as before, if you have questions, type Q in the chat and I will get to you when you do that. Alan, go ahead.
That was a really nice talk. So one of the issues which we've hit in Servo is that we do a fair bit of typed units for doing things like, you would not believe how many different notions of a pixel there are in a browser. It is quite horrible. And the problem that we've hit is that as long as you've got one team or a small number of people working on a bit of software, it's fine because everybody can agree about what the units are. But then the instant you hit somebody else's software, it's like either everything is untyped, which is the common case, or they do actually have typed units, but they've got a different notion of what the units are. So I was wondering if this is a problem you've hit, and if so, how you've dealt with it.
That's a great question. No, we haven't hit that problem. I mean, one thing is that some of these kind of things tends to be that, like, academic science code it's written by a very small number of people. So there's not this kind of software engineering teams kind of issue, and there tends to be quite a lot of agreement about what the units are, because they use SI units for things, and it's like, well, we're doing this based on this paper about this plant CO2 production model, and it involves these things, and it tends to be that there's an external reference, right? There's an external reference point. It's not just we're inventing some unit to characterize some abstract concept. It's like, no, this is really newtons per meter cubed because it's a unit of pressure, things like that. So that at least there's a kind of external guiding semantic basis, which I think probably avoids some of those issues in the science setting. But one of the things that we found, which was kind of hilarious, which I sort of flashed up, was that we found one bit of code that mixed Kelvin and Celsius, like arbitrarily. And well, in a sense, Kelvin and Celsius, centigrade, they are the same, because they're the same scale. It's just translated. But it was just so as long as you don't care about the absolute value, as long as you don't, it sort of didn't make a difference. We saw this as weird, and we thought, they probably don't care about this. And we talked to the scientists. They're like, oh yeah, it's fine because it's the same. It doesn't matter. So I suppose that's perhaps the analog when you have units that are kind of just translational offsets. Something I should say is that there is like tons of different approaches in this area, and in fact at PLDI this year, at UPSLA this year, there are, I think, at least 2 papers about units of measure in some form or another. So that's cool. Like, people are still thinking about it in different settings.
Excellent. All right, Michael, go ahead.
Great talk, thanks. I'm wondering if we could turn this problem around for a moment and think about, okay, of all of the challenges that programmers doing scientific programming have, which ones are addressable by type systems? This is presumably a subset of those. And where should we be looking next? What are the next steps in this research to help scientific programmers do their work more effectively and more safely?
So one of the things that when we were doing the year with the Met Office, a lot of the stuff that we ended up implementing in our tool was basically they had a style guide of things that are bad that you shouldn't do. Things like absolute equality on floating points was one that they said, like, this should never happen because, floating points and equality is like, what are you doing? So they said, this is our style guide because we know that these things are bad and sources of numerical instability. What we just need is a tool that goes through and checks that we haven't done that. So there are a lot of like domain-specific code smells that they wanted essentially a linter tool to like check, has this or has this not been done? One time we built a little prototype of like a Hoare logic refinement, like Hoare logic assertions, pre and post conditions, to say things like, oh, this variable is between these values. And we showed them that, and they said, that's absolutely magic. That's amazing. That's what we need. But of course, we all know that deductive frameworks are very difficult to work with in practice once you hit loops, and you have to like come up with loop invariants and things like this. So in small examples, we can let them play, with like simple pre-post condition things. They're like, oh, this is super good. But it was like scaling up to fit in their their world was difficult. For a long time, I've been convinced that sensitivity analysis would be something that's really important, like kind of stability and robustness analysis. There's been some work on that in our community, but I don't think it's been really applied to sort of numerical scientific style code. I mean, these are my kind of observations, I suppose. There are lots of other things to do with the right use of arrays and so on. I mean, I suppose I could go on about this for a while, but yeah.
Okay, thank you.
Sweet. I'm finding out if Luke wants me to relay that question he just asked in Discord.
Yeah.
Do you see it, Dom?
Yeah. So what is it that makes the studies too hard to run? Is it access to users or people to run the study, or need too long studies to generate answers that are interesting to you?
Excellent.
Access to users is difficult, for sure. People to run the study, also yes. Yeah, I think those are the two issues. I mean, we could certainly design. You'd have to. It's very difficult to do studies that involve large legacy codes, because you have a very small user base of people who understand enough to actually do things with that code. The good places to do that would be things like the WRF model, WRF, because that is used by a lot of people. It's open source. Be things like that. Yeah, it's incentivizing and then controlling controlling the variability, I suppose, in the user studies is difficult. And then, yeah, designing experiments well. I mean, it's something that we thought this would be great, but we just don't have the resources for.
Yeah, so the reason that I asked the question was a couple of fold. One of which is I think studies are often a lot cheaper than people imagine. You can get a lot more useful data out of very small qualitative studies than people expect, and so those are studies intended for formative research rather than summative research, so kind of idea formation and further design generation. I think we've seen this in a couple of the different papers today, of people moving directly to kind of randomized control trial quantitative evaluation models, and that's only one very particular way of addressing what usability properties of systems are like. And then the second is this feeling that it doesn't make sense to run user studies unless you're studying the thing that's interesting, which only occurs in really large, really complex legacy code bases. But actually, a bunch of what limits adoption is not, is it powerful in really hard problems? It's, is it easy to get to engaging with a bunch of, with problems of that complexity? So I think on a number of axes and a number of talks today, we're seeing a case where kind of what's called discount usability methods might actually return substantial usability benefits. I'm happy to chat with more with you. I don't want to derail this, but it's just an observation of a pattern that we're seeing.
Yeah, no, I really appreciate that. Yeah, I think it would be great to be able to do something in that space. With other work that we did kind of analysis that was based on kind of, you know, non-human involved things. So like large scale analysis. Well, we did analysis over GitHub histories, and trying to look at places where our tool could identify a change, actually identified the change which was fixed by their bug and things like that. So that kind of tells you like, oh, it would have helped if they'd used it in that case, maybe, but you know, it's sort of yeah, we've done things like that in the past, and large scale code analysis, pattern analysis style things, but
Cool. I'll wrap up with one last question, since Chris said that their question was taken by Luke. Along the lines of like non-quantitative studies, I really do wonder how much your users actually trust your tool. So I sort of think about my experience in industry. If you're aware of the tool Prefast from Microsoft, the static analysis checker, right? I had to deal with that in a previous life. And you know, it's a general purpose static analysis tool that has lots of false negatives, the bad one, right? And generally speaking, right, it works to a point, but the cost of using it and the general distrust of like, you know, the errors that you get, oh yeah, most of those are bad, ignore them, right? But it seems like you've hit a sweet spot here where units of measure, it's a generally analysis that we can do pretty reliably. And on top of that, your user base seems generally receptive to it too, which is great. And I think that's sort of when I actually wrote down a question like, do you actually add the annotations to the code? And then you immediately said you did. I was like, oh my gosh, your users let you do that? That's crazy. Because, you know, if Prefast, for example, started dropping in annotations, that would be horrible because most of them would be bogus, or worse yet, the users would think they're bogus and would not enable that feature. And so I guess this is mostly just like, I'd be really curious to see a study where you just like, you know, ask people, you know, do you trust the annotations that you get? And I think that's a good metric of usability to consider.
Yeah. I mean, they're just comments and people can delete them if they want, you know, kind of thing. I mean, one thing that we had thought about trying to do is also trying to extract the existing annotations that people typically have in their comments and trying to sort of do a little bit of guided learning and a little bit of smart things to try and like turn those comments into like, oh, and here's the spec. Because we just observed it was something that people wanted to do anyway. They were doing it informally, so it was just sort of like, well, they won't mind if we formalize it, kind of thing.
Cool. All right. Well, I think that is it. Thank you, Dom. I'll clap again. Yay. Yeah, that's it for the session. Michael, Chris, any final notes before we break?
I don't think so. Thank you, Peter, Michael, for sharing.
Yeah,
thank you to the speaker. Well, thank you to all the speakers. It's a really interesting discussion, and we'll resume in 40 minutes.
And now I hide my video. Bye.
Hi, Gabriel. Are you around?
I am indeed. Oh, there we go.
I
made a
do you want to
yes,
test out screen sharing or anything like that?
Yes. Let me get that going for you here. Okay. All right. Can I be seen and can I be heard?
Yes to both.
Fantastic. Does this now go to full screen?
Yep, that's pretty full screeny.
Yeah, as full screeny as it gets. That'll be fine.
So let's just leave it for a couple of minutes for other folks to get back from the break, and then we'll kick off.
Sounds good.
Great. Looks like a fair number of folks are back. So, Gabriel, I'm looking forward to your talk.
Thank you very much. So, this workshop asked for position papers, so I'm going to stake out a position. So I'm going to say that programming languages shouldn't and needn't be Turing complete. So I'm going to make this argument, and I'm going to say 4 things, roughly. One, that Turing completeness is largely unnecessary from a specific theoretical standpoint. Of course, there's a caveat there, but it's an interesting standpoint to consider. And number 2, a lot of software engineering that happens in the wild, even if you say you don't have a good Turing incomplete language to solve this or that problem, a lot of stuff that happens in the wild is surprisingly simple. And number 3, we can make fairly straightforward Turing incomplete constructs that capture many of these simple use cases. And finally, I'll say that this is a great basis for building a practical and popular language with really strong whatever you want to add to it. So it's a good basis for adding a lot of the fancy things that we've been talking about. Why would we want this? Well, there's Rice's theorem, which basically states we can't prove things for all the programs in our language, which are non-trivial, if our language is Turing complete. And conversely, if we are Turing incomplete, and since Rice's theorem relies on reduction to the halting problem, we have some hope that we actually can become a lot more complete in the things that we're proving about our programs. And this makes sense because there's going to be less edge cases, and it creates, I believe, a virtuous cycle. So there's lower cognitive load for the person who's implementing it, for the person who's using it. And like one catchphrase I think there is less leaky abstractions in making sort of smart programming language features. Yeah, that's covered in the next. So what we already have in terms of Turing incomplete languages is, to some degree, we have SQL and we have some proof assistance sort of stuff. SQL and then some data log languages. So query-ish languages, which often use the Turing incompleteness for some variant of optimizing the code behind the scenes, optimizing the queries. Largely, and then you have a more interactive environment where the manageability of the language in which you're trying to express your proof is useful for giving you lots of feedback about where you went wrong, or being very expressive in the things that you're trying to prove. So the goal is to bring both that sort of verification aspect and that optimization aspect to general purpose application programming. And there's a historical pattern here that I'd just like to point out quickly, where we've gone from having a thing that you can do, and it's not just writing programs that don't terminate in a Turing complete language, it's also like things like memory, manual memory management, even just a step of getting rid of goto was something where we removed things and gained from that removal of power. And part of that is that I think this step of removing things can enable new application fields. And there's some use cases which I'm particularly interested in the machine learning realm. There's stuff you can do, where you kind of want a sort of dependently typed system, or you want to have really good feedback about how this is going to act on your GPU. And then, if you had a better constrained language, you might have an easier time doing some sort of like TLA plus style checks of whether it's Byzantine fault tolerant or something like that. And so blockchain stuff loves it. And then also, if you go back to the Rice theorem, if we're able to prove that certain bad conditions can't happen, it's easier for us to build an efficient sandbox. So here we come to some claims. I did a small literature search, literature review, and I'm very open to more examples here, but I only found 2 examples of a problem known to computer science that we cannot solve without a Turing machine or a Turing equivalent system. One is simulating a Turing machine, and the other is the classic variant of a self-interpreter. There's actually a more recent result that if you don't represent the code as sort of a Gödel number thing, you can actually kind of do self-interpreters. But so there's, we can represent, we can run the Ackermann function on Gödel system T. So we can compute a lot of stuff theoretically on Turing incomplete languages. The problem is it might not be efficient, and specific efficient algorithms, you might go, well, I don't know. I bet there is some Turing incomplete language which somebody could come up with which solves my specific, I don't know, quicksort or my specific NP complete problem efficiently. But the ones, it's hard to build those potentially. Yeah, that's actually kind of true. And I would say, while that is true, there is a glimmer of hope. Namely, the arc of history has been, in the beginning, we were doing a lot of more real algorithmic things, whereas nowadays, a lot of people don't actually need to implement the kind of things that they ask you in the algorithmic interviews when you get hired for your tech jobs. Actually, they build a lot more trivial algorithms and use libraries which get combed over more sort of intently to do most of the more complex algorithmic tasks. So to kind of back this up a little bit, I did a small informal study. I just went to GitHub and I made 2 searches, like gathered 2 repos and just went through them. And these were in Python and Java, and I think one in JavaScript. Yes, in JavaScript as well. So these are, fairly contemporary repos, not too large, and it just like from the first page of what came up in GitHub search. And I didn't find in those repos any algorithms which I thought, oh, these will be hard to convert to a Turing incomplete language. I need to have some system. Yeah, I didn't have to assume any system of sort of proving complex things in the background. There was like one while true that really shouldn't have been there. So, there you go. And this makes sense because a lot of the higher level programming languages, such as Java, Python, JavaScript, they really have been adopting terminating control structures like list comprehensions or looping for each loops, as opposed to just open looping. So this is how you do it. If you want to start from a small, simple base case Turing incomplete language, you just remove the while loops for recursion, and you mainly, in this case, before adding, so this is how would you build such a Turing incomplete system without assuming an advanced verification system in the background, without assuming that the users need to be smart about the correctness of their system, with the idea being that you might then add that on later on, but let's start simple. So you use, you can add these things later on of, you can have like escape hatches to Turing complete system, or you maybe have some way of writing your code in your Turing incomplete language, which is inefficient, and then proving later on that's equivalent, that sort of stuff. But to start with the simple bit is, I think, something that's undervalued here. If you want to do it for a functional language, there's a certain list of things you can do here. I think it's fairly obvious. You can also do this for an imperative language. And I think I want to go into one example here. So Guido van Rossum, the creator of Python, complained about reduce being an unpleasant, there's a quote from him where he complains about reduce being an unpleasant construct. And to some degree, I agree with him, but I think it's mainly just a syntactic problem. And actually, even this code that we're looking at here on the slide is slightly Python-esque. And it shows that, Python has reduce built in. It's basically a for loop with one state variable that gets updated. So you can make it more obvious here that there's a state variable. And you can use, now to go back to making, because if you go to replacing recursion, getting rid of first-class functions, say in an imperative language, or at least getting rid of recursion in a functional language, you need to use reduce a lot. So let's say if I were to implement a list, I would look at this and I'd somehow make myself a nice macro that represents this kind of reduce semantics, this kind of syntax. Here's another case. You can, so there's one way of looking at algorithms as being either structural or of a generative kind of recursion, where if you're structural, you're iterating over a collection, as opposed to generating new state until you reach some target and then you return it. So in this case, this Euclid's algorithm, you have a case of kind of a more complex, so you're iterating over just a range. You know that it's bounded. You're iterating until you reach the condition which terminates this loop. And because it is bounded, we can do this in a very simple system. But you could imagine, of course, if you had any kind of types or any kind of other system of reasoning about your code, you might be able to expand on this and make for more complex conditions so that you know, okay, this actually will terminate. We can run this with a more complex expansion operator. Here, another case just of running a nested reduce. So if you just have a normal reduce operation and you want to handle an arbitrarily nested data structure, that doesn't work. So you need to expand the semantics a bit. Here we have a keyword, a nested keyword, which just means I just want to iterate over all the nested items of this thing, and it's going to give me the whole thing first and then the elements of it. What you do here is you have some sort of direction, special keyword. You could express that differently. It's not a great way of doing it, but I think it's possible. It's possible to definitely do recursive traversal of trees, of nested data structures, and you can come up with this sort of syntactic sugar to make it doable. And it doesn't happen that often in application code. So I think it's definitely a bearable sacrifice for what you get out of it. Now, in conclusion, in my opinion, simple and usable Turing incomplete constructs as a base are possible and are desirable. From there, you can build up to more complex systems. But what I really want to bear in mind is that the first goal is you want to win over everyday software engineers. And for that, I'm pretty sure you need these less leaky abstractions. You need to make sure, as was stated in the first talk today, is you want to make any kind of checking that you're doing in the background really automated. You want to be living in a situation which is analogous to, say, the JVM. The JVM has garbage collection. Many retail programmers never touch the garbage collection of Java, of the JVM. Maybe they're using a different language that targets it. But then there is a whole swath of people who know very much about the garbage collector because they have to touch it in anger. So you want to have a situation like that where whatever verification or optimization or checking for runtime complexity you're doing in the background, that it can be done automatically without sharp edges for at least as many people. So that's why starting small, I think, is a good idea. And then I think it's a great basis for building up a lot more features of that sort of background system. And that's it. Thank you very much.
Thank you. Great talk, and nice to start a bit of a provocative discussion here. So who wants to go next in response to this? Oh, I'm seeing on the list, Alan Jeffrey.
Okay. I am very sympathetic to this argument. Like I write a fair bit of Agda code, so I'm used to fighting with termination checkers. The problem that I've seen with systems like that is that there are algorithms. The kind of canonical ones are anything that's like kind of minimum spanning tree, where you're like marking a graph as you traverse around it, or web servers, where what you end up doing is you end up introducing the notion of fuel. So you calculate the amount of fuel that's going to be required for this. So like for a minimum spanning tree, it's the size of the graph. and now you use a unit of fuel every time you do a step, and that's fine. But then either you have to prove that you provided enough fuel up ahead of time, or which is a proof obligation on the programmer, or you have to deal with the case that you ran out of fuel. And both of these are annoying. So I was wondering if you had a thought about that.
Well, you're right. Though that is both difficult and potentially annoying. I have an example of something like that, where it's easy to prove that you have enough fuel, like the Euclid's algorithm. Like, you know that you're right, but in most cases you can't. The fact of the matter, though, is that I think there are enough people who don't have to do those kind of tasks. So I would approach this as a more of a social question. Like, how can you get to sufficient mass? Like, if lots of people are using things, like we have been able to take JavaScript and make it efficient. So if enough people use something and then start complaining, well, I need to do this thing, but I can't actually do it well, then you're in a much better position to build the kind of fine-grained evolution steps that are needed for that. Like, maybe you need to have a library that allows you to check those sort of things more efficiently. Now, if you have a very simple system to build upon, then you are in a better position to make a language where verification is sort of pluggable, where somebody else can, without too much cognitive load, build a checker for this specific area, and then other people can reuse it. That would be my best response, I think.
Thanks.
Thanks. Jonathan.
Yes, nice talk. Very interesting and provocative. One comment I would have is well, I think it builds on what Alan says. I've built a lot of programming tools, and a lot of them are based on convergence. And so, there's good theory that says it converges, but it's really hard to express. Another good example, maybe in this same domain, is any kind of GUI or server, really, where any given response should terminate, but the overall thing shouldn't terminate, which of course we can handle through libraries and so on. But it does make me wonder, maybe there's constructs, yes, that are Turing incomplete, but maybe we should also think about constructs that maybe there's other kinds of enforcement, right? There could be dynamic enforcement that things terminate, for example. I don't know. Yeah. Can one broaden the scope of what you're proposing to include things like, of course, you can't technically dynamically termination check, but you can certainly put a timer on things.
Well, the good news is that I actually personally don't necessarily think that termination is an issue if your goal is to have it not terminate. Then it just goes back to, you still want Turing incomplete semantics, so you still want to prove things about it. You just then go to a system that is basically, it's an open loop over the incoming events. I should have included that in the slides, because yes, I think that's an important aspect, that for those kinds of applications, for GUIs, for servers, you want to be able to just have like this open event loop, while every single execution, of course, is terminating. That is something you need to enforce.
Is what you're saying there that, for example, you could, if you were in a rendering loop, then yeah, you'd want to make sure every single frame terminates, but the loop can just go on forever.
And you maybe would want to also write a verification library that makes sure that, under X conditions, you terminate within a certain time. And this is one of the nice things of getting around Rias's theorem, that it's within our reach to do automatic, like, O of X time complexity inference. So that would be nice.
And I think we just have time for one last question here and then over to Discord for this piece of the discussion. So from Will, please.
Okay, so one thing in this vein that I've been thinking a lot about is how many primitives you give somebody to think with and to implement with, and then the relationship between the number of primitives, the amount of effort to construct any individual program, and the number of tasks that it takes to solve. So for example, one of the great parts about for loops and if statements is that once I teach you those two things, there is a huge amount of data structures, transformations, and processing you can do. And it's easy to say like, well, we should be teaching people map and filter. And I'm 100% in that camp. But at the same time, in terms of time efficiency, you learn two things and all of a sudden you have this huge range of operations available to you. There's a lot of value in having a relatively small basis of thought, which then you have to engage in the higher level problem solving of, okay, you know, how do I do all these things and turn them into for loops and if statements? But people are pretty decent at that, right? So I guess my concern is that if we focus more on Turing incomplete languages, that naturally shifts towards a much wider vocabulary and, you know, more towards having specific words to do all the individual things rather than on these more general purpose operators. And I'm just curious to hear your thoughts on that question and its impact on Turing incompleteness.
I think you're completely right. And I think that is a cost that you incur. You can mitigate it to some degree from a theoretical standpoint by saying, look, I'm going to build a system in which it's easy to build primitives. But that is kind of at a level which, when you're talking about teachability, is kind of not that great, right? And so I think it's a real trade-off that you're facing that is often makes this sort of feel uncomfortable to me, coming from kind of minimal languages myself. Yeah, I agree. It's an issue.
Yeah.
Great. Well, thanks so much for this. Great discussion. Let's thank Gabriel again, please. And Michael, over to you for setting up presentation. So we briefly had a screen share that worked from you. We're now down to just a vertical white bar. And we're back. You are muted, though, if you're already speaking.
Thank you. Sorry. How about now? Okay.
Great.
Sorry about
That's
that.
perfect. Thanks.
Okay. Thanks. All right. So today I'm going to be talking about work that Jonathan and I did in the context of a course that Jonathan was teaching. So the question here is, okay, how we can see how user studies can lead to language design insights quickly, in this case, in the context of a course project. The context here is of user-centered design of programming languages. So the idea is rather than disappear into my cave and then coming up with a design that I want to test, I want to actually get feedback from users and then iterate. So you know, we start by understanding users and the tasks they're trying to accomplish, and then we come up with some design, but then we iterate on the design using a collection of methods, right? Not just the formal methods and case studies that people are maybe most comfortable with, but also qualitative studies in which we ask participants to do tasks, and quantitative studies like randomized controlled trials. So the question is, you know, can we do this in a fairly lightweight fashion? Lightweight enough that we can get students in the context of a course to you know, get insights about their programming language designs. The system that we had proposed during my PhD was called Pliers, the Programming Language Iterative Evaluation and Refinement System. And the idea is, as I described, that you iterate, you see in area 4 here, around your design that you come up with using these empirical methods. And in this work, we were interested in evaluating Pliers in a limited context. You know, we developed this tool during our research, and the question is, can anyone else use it effectively? And so our starting approach is to teach some methods to students and see what they can learn. So today I'm going to be giving an experience report about using these methods in order to evaluate programming languages in a classroom setting. The context is a course on language design and prototyping that Jonathan Aldrich was teaching. This is a course for kind of juniors and above, at least if you go by the course number, people who already had a fair amount of background writing programs. And so the course included a project which went like this. There was a language proposal. The students were asked to do a conceptual analysis according to Daniel Jackson's approach to design by concept. The students were asked to design a language semantics. They're asked to design and execute a user study, and then they could use that to iterate on their final design and build a prototype. And we separated the user study, design, and execution into 2 different phases so that we could give them some feedback on their initial proposal before they went and ran their user study. So in order to make this practical in the small amount of time that the students had, we focused them on 2 particular methods: usability studies and natural programming. So I'm going to talk briefly about what these are. In particular, natural programming, which is a technique that maybe not everybody's familiar with, is a way of trying to find out how people might write code naturally, that is, without any training. So I'll give an example here. Here we have a diagram from John Pade's PhD thesis where this work was initially developed. You give, in this case, children some pictures showing a behavioral specification. In this case, the children were asked to write code for Pac-Man. So here's some instructions for what Pac-Man should do. And then the children were asked, please write a statement that summarizes how I, as the computer, should move Pac-Man in relation to the presence or absence of other things. So the idea is, don't teach people a programming language and then see what happens. Instead, actually just get people to use their existing vocabulary and language to write down how they should specify some program. In usability studies are maybe more broadly understood. The idea is you get it's a low-cost way of identifying some usability problems in your prototype by asking people to do some tasks given a prototype. We taught these methods to students in 4 80-minute class meetings. We had IRB approval for the study, and we obtained informed consent from the participants. So the students were just asked to recruit convenience samples. They recruited whoever they could get access to. The students were all agreed to co-author the paper. We were careful to do this after the course was done and all the grades were assigned. So there was no coercion of the students to participate in this research. Here are the languages that the students came up with for their projects. You can see they were invited to do the work in groups, so some of them chose to do that, some of them chose to work individually. So I'm going to be talking about several of these languages and what the students found as they used these methods in their design projects. One thing I want to point out here is the wide variation of different kinds of contexts people chose, ranging from a functional language for writing concurrent code to a programming language for automatic knitting machines. So some very domain-specific languages, some very general-purpose languages. The students were encouraged to work on whatever they thought was interesting. So I want to first talk about the natural programming results for the students who did that. And then after that, I'll talk about the people who did the usability studies. So the student was interested in a syntax for sending messages between threads. So they asked participants to write code to send messages between threads. You can see how Go solves this problem. They didn't give the participants this sample code. I'm just showing you the sample code here so that you can kind of see what an existing solution to this problem might look like. You can see here, is my cursor coming through? Maybe someone can tell me.
Yes.
Okay, great. We have this messages channel. So we make a new channel that is good for communicating strings here. And then we're going to send ping along this messages channel. And then here we're going to receive a message along the messages channel. So you can see they have this arrow operator that's used. Interestingly, nobody invented a new operator among their participants. People use the word send and receive instead. So it seems like, if you take send and receive as the natural solutions just because that's what people proposed, there seems to be some trade-off between naturalness and concision. On the other hand, other studies with non-native English speakers have suggested that actually keyword choice is not a big factor in usability. So it could be that concision is more important here. and we should not focus on the results of a natural programming study for choosing keywords. Again, this is all fairly, this is a small study, so I'm not trying to come up with, final guidance on how to use natural programming, but I'm trying to show you kind of what we observed in our study. So for the knitting programming language, the student focused on how to specify cables. So a cable is a particular construct that you might knit when you're knitting a garment. And the idea is cables tend to be a fairly hard thing for people to specify, at least in the student's experience. So interestingly, as a result of the kind of constraints imposed by the pandemic, the idea here was to do a limited corpus study rather than recruiting a bunch of in-person participants. They were able to gather a collection of patterns. They focused on patterns by one designer because that's the corpus that was available. And the observation is that a lot of the instructions took the following form: slip loop count to hold on front or back, followed by some stitch instructions on the main row, followed by stitch instructions on the held stitches. And so you can see how using this corpus lets us identify a natural way for people to specify cables. So some design decisions in the language that came out of this, there's this needle identifier clause that can be used to specify needles or queues of loops. When I say loop, I mean knitting involves sequences of loops that are held on needles. So loops are an important construct when you're talking about knitting. There's a to phrase which places loops on a particular identified needle, operations to needle identifier in front or back, and then a from phrase which consumes loops from a particular needle, operations from needle identifier. So you can see how in a particular domain, a corpus study was useful in coming up with the syntax for this language. Another study was about analogical reasoning. First, participants were introduced to the concept by asking them to practice analogical reasoning. For example, bakers, the watchmakers of noun, you'll find them working on watches of their own. Verb the noun, and verb the noun. And then they're asked to propose a syntax. So some of them use kind of Mad Lib style syntax like you see above. One interesting result, based on the example, the integral like a noun, verb spaced into tiny noun plural. What they proposed was the syntax here: integral, comma, question mark, colon, question mark, arrow, question mark, meaning if an integral acts on something, what else acts on something in an analogous fashion? So you can see how some people were able to come up with kind of symbolic syntaxes there. That student said, "I'm glad I did a natural programming study rather than a usability study of an existing system, since it afforded a closer look into what kinds of analogies would be useful to query for and what expectations people would have for such a system. Staying close to the metal of English and writing questions gave me more insight into the needs and quirks of potential users. It helped avoid the bias of a more constrained set of problems that I'd choose for a concrete usability study." So it's sort of a nice summary in that natural programming lets people kind of self-direct a little bit how they're going to do the work, as opposed to usability studies, which tend to be a little bit more narrow. All right, now I want to talk about some usability studies that people did. One project was on what's called block element modifier notation. This is a convention that some people use when they're writing CSS code. So the idea here is that you have blocks, which are high-level constructs. You have elements, which are contained inside blocks. They can't live on their own. And then you have modifiers, which modify properties of blocks. And so the proposal is for a language that the student called EMOS to enforce this BEM notation. And so the idea is, instead of people following the convention manually, they would write code in this language, and then the compiler would automatically generate the appropriate CSS. So for example, you might have a block with a name, and then an element inside the block, and then some modifier that can be applied to the element. So this student chose an internet-based tool. I use the word survey here because it looks sort of like a survey, but the point was it stepped people through the process of training people in these tools and then asked them some programming questions. So you can see here this task that lay out a CSS structure for the following components, and then write code in either CSS or EMOS. And you can see the structure here, right? There's an image at the top, and then there's a title, and then there's some text, and then there's a button. And you can see there's a white version here, and then there's a black version here. Other than that, these two are identical. And the most common mistake that was observed here is that people neglected to specify the modifier elements. So you can see a typical correct answer has a black modifier, and then image, title, content, and button elements. And then a typical wrong answer would omit that. So the question is why? And the answer is, well, we don't really know why, because when you do a survey, you don't get that kind of depth, right? So an important takeaway here is if you're going to do this kind of study, it's really useful to use think aloud or other kinds of techniques to understand why people make the mistakes that they did. Another student was working on an IoT language. Participants were given example code and documentation for a language for programming IoT systems. So these are distributed systems where there are many different nodes, and you want code to run on sets of nodes. And the student was interested in studying how people specified when code would run, right? You could imagine, because these are real world kind of systems, you want code to run when things happen, when the doors opened, when somebody enters the room, when the temperature exceeds a set point, that kind of thing. But a lot of questions that the participants had were about the delineation of where code runs, not just when, but where. So this really helped the designer here focus in on important language design questions that needed to be resolved. So in the revised language, the answer to the question of where is intertwined with the question of when. The student really realized that you couldn't separate those completely, as was the original plan. There was a project on describing two-dimensional puzzles. So think of Sudoku, for example, where you need to describe rules regarding features of 2D grids. So imagine you're trying to implement Sudoku in some programming language. How do you do that? So they gave people an example of how one might do this in their prototype language, which is a functional kind of language. And you would expect that people would write functional code because they were given a functional example. One participant who said their favorite language was SML, which is of course a functional language, wrote imperative code with a loop and return. So this is kind of interesting, right? One of the complaints about natural programming studies is that people expect that surely people will just write in whatever language they are most comfortable with or most familiar with. But in this case, that's not what we saw, right? The participant said they were most familiar with SML. They were given a functional example, and yet somehow they decided imperative code was the right solution for this problem. Also, I want to note that somehow this transitioned smoothly to natural programming, right? The participant was not asked to write this in any possible way, right? They were asked, here's an example, please follow the example. And somehow this turned into natural programming. So the distinction between a usability study and a natural programming study may be a little bit more fluid than we had previously imagined. So you can think of maybe newer study designs that are a little bit more continuous. And yeah, again, it seems that people's bias toward preferred languages can be overcome in particular experimental situations. So some interesting results. It was useful to use corpora for doing natural programming studies. That's not an approach that we had seen anybody use in the past for doing this. It's important to get insight into the process in order to get actionable advice for refining language designs. It's not enough to just see what the behavior was. You need to understand why. Natural programming techniques are not necessarily poisoned by prior experience. You may get new results even with people who have significant programming experience. And even if you somehow give them hints in a particular direction, they may not take your hints. And finally, usability studies can be useful in early stage work, as in these course projects, in order to identify where effort should be focused in the design process of the language. So thank you very much, and I look forward to any questions.
Thank you very much, Michael. And does anyone have an immediate question coming up? Molly.
Hi, Michael. Thanks for the great talk and the interesting course-based study. So with natural, I may have missed this, but with natural programming and usability, the choice between which one they could use in the course project, I'm interested in like the intuition behind that. So like, why did they pick one or the other? And then also for these students, were they like HCII students? So they had previous user study discussion, or was this just like your average software engineer student? Because a lot of people have communicated to me like they'd like to do these kinds of studies, but they don't know about it. And obviously you taught them, but I'm curious about that intuition part.
Yeah, so there were typically CS undergraduates. There was a few other people mixed in. For example, one of the students was an HCI PhD student. So they obviously had kind of a leg up in, doing these kinds of studies. I don't know offhand what the demographics were. Jonathan, do you want to speak to that?
Yeah, it definitely was mostly undergraduate CS majors. There were a couple of graduate students, only one of which was an HCI PhD student. So I think part of, obviously we had the students that came to the class, but part of the point of doing the study was, can we teach this to undergraduate juniors who don't have any prior HCI experience, and have them do, get interesting results, right? These are not the results you would get after a whole course of training. We had just a few lectures on this, but I thought it was encouraging that we did get they were able to get interesting results. And hopefully the language designers of tomorrow, even if they don't all have a PhD in HCI, can use some of these lightweight methods.
Now to your first question about the choice of natural programming and or usability studies, I think we kind of encouraged them to use whatever methods were appropriate for the questions they had. So if they were sort of trying to figure out what to design, then a natural programming study might be more appropriate. If they already had a design in mind and they wanted to know what the usability challenges were, then a usability study might be more appropriate.
Awesome, thanks.
Thank you.
I wonder, one of the things that we see happening within the psychology of programming community quite often is that people running their first studies come across the same kind of broad genre of problems as the last set of people who ran their first studies. Could we use this to start collecting a place where we talk about our accumulated wisdom on how to run these kinds of studies?
Yeah, that's a good question. I feel like we're really good at cranking out individual papers that say what we did for that particular project, but in terms of like a textbook, I think we're not there quite yet. Also, not that many of these have been done for programming languages, so I think we're kind of still figuring out what the guidelines should be.
Chris.
Yeah, thanks for the talk. This is incredibly cool. I'm impressed about the success of this class, and the results you discussed are really inspiring and neat. I wanted to know, I guess, a challenge that folks can come across that maybe this is one of the things that I'm curious as what sorts of things Luke was alluding to in terms of common challenges people come across again and again when they do their first user study. One thing I might expect is that people would find that, syntax and sort of surface level issues are much more salient for users than perhaps the underlying semantics of the language that they're proposing or providing for use. And I wonder if you have any recommendations either from this work or from your prior work on kind of how to design a study to get at sort of deeper semantic issues.
Yeah. So, the first thing people figure out when they design a user study the first time is that the materials are bad, right? The tasks are not well defined. The documentation doesn't make any sense. So that's the first thing that people have to get through, including me, right? Like even with experience, you get these things wrong the first time, and that's why you have to pilot these things. Now, in terms of ways of getting past the surface, what we've done in some of our work has been to try to include enough training as part of the study that you can get people past the initial barriers, and then sort of pay more attention to, at least in terms of the research questions, at what happens afterward after you've done the training. So if you can train somebody up in doing something and then afterward they are successful, right, then you can reason about the kinds of successes they have. If you try to do some training and then they're still struggling and you never get them to the point where they were successful, it's hard to argue that you learned a lot other than, so far the training materials I have don't work with this population, right? I mean, it could be that fundamentally the thing you're trying to teach is hard and it's going to take more time. or it doesn't have to be that hard, but your materials were confusing. Right? And it can be hard to tell the difference between those two things until you have tried even harder to refine your materials. One of the things that we found was that if you just give people some documentation, and maybe this is obvious to people who teach classes regularly, I don't know, I'm not in that boat yet. If you just give people some documentation and you ask them to read it, and then you try to have them do something based on the documentation they read, then it's almost as if they didn't read the documentation. It's like they didn't absorb what they learned. Yeah, everybody's nodding, right? So, you have to do something during the training phase to force them to practice using the material. Otherwise, they get stuck, very early in the tasks with things that, were documented, and, they just don't even seem to be aware that it was documented, even though officially they said they read it.
To the point that Michael made about, people not being good at this the first time, I think important to the success of the class was iteration, right? We had them design materials, we had them prototype them, we gave them feedback as instructors who had some experience, and then they did the study that you read about here.
Cool, thanks.
Thank you.
Great. So I'm conscious that that's pretty much out of time, but let's all thank Michael again.
Thanks.
And Chris, I think you're leading the discussion section of this, if I'm right.
Yeah, so we are gonna sort of transition over to discussion at this point. We technically, I think, only have until 5 o'clock, but of course, I think if people want to stay a bit longer, you're welcome to. So what I was thinking is that it would make sense for us to maybe propose a couple of topics that people saw come out of the talks today that you're interested in discussing further. And you can go ahead and, if you want to right now, just like propose a topic in the chat window, and I can I was going to make a Discord voice channel for each of those topics. I guess unless everybody just wants to talk about the same thing, which I think would be unlikely, but I'd be happy to set up those voice channels. And then I suppose if there's enough people still around in 20 or 30 minutes, then we can reconvene and report out, or just report on those discussions perhaps the following day if people kind of trickle out. So does anybody have, I was suggesting, I mentioned in chat before, we could do Zoom breakout rooms if people prefer that. I think there is the option to set up breakout rooms where you can self-select into the room, but you have to be on the most recent version of Zoom in order to do that. So I thought Discord might be a simpler way to go. But yeah, so does anybody have what would y'all say, feel free to suggest things, like what were some topics that you thought came up more than once today in the talks that we saw?
Well, one simple proposal might just be to create 3 rooms for each category that we had today. So formal methods, types, and language design.
Okay.
I'll put that out there.
Yeah, sure. I'd be happy to do that. Are there any additional, I'll just make those channels, and then if there are any other suggestions for voice channels, I can add them. So is it formal methods, types, and language design?
Yeah.
All right. Well, okay. I suppose without further ado, we can adjourn to those rooms and discuss those topics, unless people have other. I guess. Oh, Michael said usability of Rust ownership borrowing. Do you think that that's subsumed by? That was in the types session.
Yeah, that's fine.
Today,
We can
right?
put that in the types
Yeah.
category.
Okay. Cool. Let's do that. All right. Sounds good. Oh, what Discord? Yes. Could somebody paste the link to the Discord in chat, just in case anybody doesn't have it?
There.
Perfect. All right.
Catch y'all on this.
One additional suggestion of context for people as you go into these rooms. I'm hoping that at the end of tomorrow we can have a discussion about kind of a research agenda for this community. And so as you have your discussions in the different rooms, you might think about, what you want to propose that we should work on. What are the highest priority questions that might have promising results? How should we organize our work moving forward?
Cool. Yeah.
Okay,
Sounds
see you all in the rooms. Thanks.
Thanks.